the weight of deep time. Tonight, we embark on a journey through the most mysterious dimension accessible to human contemplation. Not a journey across space, to distant galaxies or alien worlds, but a voyage through time itself. Deep time, geological time, the kind of time that renders human civilization not merely brief, but nearly invisible. We begin with a question that emerges not from speculation, but from the mathematics of existence on an ancient world. A question that arises when we confront the true age of Earth and the incomprehensible brevity of our own presence upon its surface. What if humanity were not the first civilization to arise on this planet? Not the first intelligent species, not the first technological culture, not the first to gaze upward at the night sky and ask whether consciousness might exist elsewhere in the cosmos. What if, buried beneath hundreds of millions of years of geological transformation, beneath continents that have collided and separated, beneath oceans that have opened and closed, there existed civilizations whose very existence has been erased by time itself? This question does not emerge from ancient astronaut theories or fringe archaeology. It comes from peer-reviewed scientific literature, from researchers asking fundamental questions about detectability, preservation, and the nature of evidence across timescales that dwarf human comprehension. Earth is 4.54 billion years old. Modern humans, Homo sapiens, emerged approximately 300,000 years ago. Civilization as we define it, with agriculture and permanent settlements, began roughly 12,000 years ago. Industrial civilization, the kind that might leave detectable traces, spans merely 250 years. The disparity staggers the imagination. If we compress Earth's entire history into a single calendar year, with our planet forming at midnight on January 1st, then modern humans appear at approximately 11:58 p.m. on December 31st. All of recorded history, from the first Sumerian writings to this present moment, occupies the final 10 seconds before midnight. What happened during the other 364 days, 23 hours, 59 minutes, and 50 seconds? The conventional narrative suggests a world devoid of intelligence, a stage awaiting the arrival of humanity. Life evolved, yes. Bacteria, plants, animals filled the seas and eventually the land. But intelligence, technology, civilization, these are presented as recent innovations, unprecedented achievements that distinguish us from all that came before. But what if this narrative, comfortable and anthropocentric as it is, reflects not the truth of Earth's history, but merely the limits of our ability to detect the past, permit the breath to slow, to deepen, feel the weight of the body settling, the mind releasing its grip on certainty? We are about to descend through layers of time so profound that human language struggles to contain them. We will explore the geological processes that both preserve and destroy evidence. We will examine the chemical signatures that might persist when physical structures cannot. We will confront the uncomfortable possibility that absence of evidence, when dealing with such timescales, tells us almost nothing about what might have existed. The universe is patient. Earth is ancient beyond comprehension. And in that antiquity, in those billions of years of dynamic, living, changing world, possibilities emerge that challenge every assumption our species has made about its own uniqueness. The Silurian hypothesis. Science asks the impossible. In the year 2018, a paper appeared in the International Journal of Astrobiology that would quietly shift the boundaries of respectable scientific inquiry. Its authors were Dr. Adam Frank, an astrophysicist at the University of Rochester, whose work focused on the formation of planetary systems and the conditions necessary for life, and Dr. Gavin Schmidt, director of NASA's Goddard Institute for Space Studies and one of the world's leading climate scientists. The title of their paper was deliberately provocative: The Silurian Hypothesis. Would it be possible to detect an industrial civilization in the geological record? The name referenced a science fiction television series, an acknowledgement of the apparent absurdity of the premise. But the content within was rigorous, quantitative, and deeply unsettling in its implications. Their question was deceptively straightforward. If an industrial civilization had existed on Earth tens of millions of years ago, perhaps even hundreds of millions of years ago, what traces would remain? More importantly, would we, with our current geological and paleontological methods, even recognize those traces if we encountered them? The motivation for this inquiry came not from any evidence of ancient civilizations, but from astrobiology. As humanity develops the capability to detect atmospheric compositions of exoplanets orbiting distant stars, we face a fundamental challenge. How would we recognize the signature of technological civilization? What markers would persist in a planet's atmosphere or geology long after that civilization had vanished? To answer this question for distant worlds, Frank and Schmidt realized we must first answer it for our own planet. And in attempting to do so, they uncovered something profound about the nature of deep time and the fragility of evidence itself. Consider the Carboniferous period, extending from approximately 359 million years ago to 299 million years ago. This geological period lasted roughly 60 million years. During this immense span, vast forests covered much of the planet's land surface, forests dominated by giant club mosses and early seed plants. These forests eventually became compressed into the coal seams that powered the Industrial Revolution. Now imagine a hypothetical industrial civilization arising during the Carboniferous. Imagine it flourishes for 100,000 years, 10 times the duration of all recorded human history. That civilization would occupy just 0.167% of the Carboniferous period. In the geological record, compressed into layers of rock, it would represent a film so thin as to be nearly invisible, without extraordinary precision in dating and sampling. But the challenge extends far beyond mere temporal thinness. Earth is not a passive archive, carefully preserving everything that occurs upon its surface. Rather, it is a dynamic churning system that constantly destroys and recreates its own crust through the processes of plate tectonics, erosion, sedimentation, volcanism, and metamorphism. The oceanic crust, the foundation beneath the world's seas, is continuously generated at mid-ocean ridges. Here, magma wells up from the mantle, creating new seafloor that spreads outward at rates of a few centimeters per year. But at the edges of continents and in deep ocean trenches, this crust is forced downward through subduction zones, plunging back into the mantle where it melts and is completely recycled. The result is striking and absolute. The oldest oceanic crust currently existing anywhere on Earth is approximately 200 million years old, found in the Western Pacific. Everything older than this has been entirely destroyed, subducted and melted back into the interior. Any structures, any chemical signatures, any evidence whatsoever that existed on the ocean floor prior to 200 million years ago is simply gone. Not buried, not hidden, gone. Continental crust persists longer because it is less dense, and therefore resists subduction. But even continents are far from permanent fixtures. They collide with one another in slow-motion impacts that last millions of years, creating mountain ranges that rise kilometers into the sky. The Himalayas, formed by the collision of the Indian subcontinent with Asia, continue to rise even today, pushed upward by forces that operate on timescales incomprehensible to human experience. But as mountains rise, erosion immediately begins to tear them down. Water seeps into cracks, freezes, expands, shattering rock into fragments. Rivers carry this material to the sea. Wind scours expose surfaces. Chemical weathering dissolves minerals. The material that once formed mountain peaks becomes sediment accumulating in river deltas and on the ocean floor. This sediment, given sufficient time and burial, becomes sedimentary rock, but sedimentary rock is itself impermanent. Tectonic forces can uplift ancient seafloors, exposing them to erosion once more. Heat and pressure during mountain-building events can transform sedimentary rock into metamorphic rock, destroying fossils and chemical signatures in the process. The cycle repeats, endlessly, relentlessly. The oldest rocks on Earth's surface, found in the Jack Hills of Western Australia and the Acasta Gneiss complex in northern Canada, date to approximately 4 billion years ago. But these are extraordinary exceptions, tiny fragments that somehow escape destruction. The vast majority of Earth's surface has been completely remade, not once but many times since the planet formed. This is the fundamental challenge facing anyone seeking evidence of ancient civilizations. Time on Earth does not merely pass, time destroys. The planet is a palimpsest written and rewritten so many times that earlier inscriptions become not merely faded but obliterated, melted, recycled into the very substance of the world. Given this relentless erasure, Frankenschmidt asked, what could possibly survive? Are there any markers, any signatures that might persist across the geological timescales under consideration? They identified several theoretical possibilities. Chemical anomalies in sedimentary rocks, shifts in isotope ratios that indicate large-scale burning of organic material or release of greenhouse gases, the presence of synthetic materials or unusual concentrations of rare elements that do not occur naturally, mass extinction events that might result from rapid climate change driven by industrial activity, and perhaps, under extraordinarily favourable conditions, physical artefacts buried in locations where sedimentation rather than erosion dominated. But each of these markers comes with profound ambiguities. Carbon isotope excursions occur naturally during periods of massive volcanic activity or methane release from oceanic deposits. Rare earth elements can be concentrated by hydrothermal processes. Mass extinctions have occurred throughout Earth's history from purely natural causes, and physical artifacts, even if initially buried, remain vulnerable to destruction through subsequent tectonic activity, erosion, or metamorphism. The Silurian hypothesis does not claim that ancient industrial civilizations existed on Earth. Rather, it demonstrates something more unsettling, that given the timescales involved and the destructive nature of geological processes, we likely could not detect such civilizations even if they had existed. Our methods, our technologies, our entire approach to understanding the past is optimized for timescales of thousands or millions of years, not hundreds of millions. Absence of evidence in this context cannot be confidently interpreted as evidence of absence. The absence might reflect nothing more than the limitations of preservation and detection across deep time, Earth's recycling system, the destruction of memory. To understand why evidence might not survive, we must first understand the mechanisms by which Earth destroys its own history. The planet operates as a vast heat engine, driven by the decay of radioactive elements in its interior and the residual heat from its formation 4.5 billion years ago. This internal heat creates convection currents in the mantle, the thick layer of hot plastic rock between Earth's crust and its iron core. These currents, operating over millions of years, drive the movement of tectonic plates, the rigid segments of crust that cover the planet's surface. At mid-ocean ridges, mantle material rises, partially melts, and creates new oceanic crust. This crust, composed primarily of basalt, is relatively thin, typically 6 to 7 kilometers thick. As new crust forms at the ridge, older crust is pushed away in both directions, creating the seafloor spreading that was discovered in the 1960s and led to the acceptance of plate tectonic theory. The oceanic crust moves across the planet's surface at rates measured in centimeters per year. This seems glacially slow by human standards, but over geological time, these movements are substantial. In 10 million years, oceanic crust can travel 1,000 kilometers. In 100 million years, it can traverse the entire width of an ocean basin. Eventually, this oceanic crust encounters either another oceanic plate or a continental plate. Because oceanic crust is denser than continental crust, it is forced downward in subduction zones, plunging back into the mantle at angles typically between 30 and 60 degrees. As the crust descends, it experiences increasing temperature and pressure. Water trapped in minerals is released, triggering partial melting of the overlying mantle wedge. This magma rises, creating volcanic arcs like the Andes or the island chains of Japan and the Philippines. The descending slab continues downward, eventually reaching depths where it is completely assimilated back into the mantle. This process, elegant and inexorable, means that oceanic crust has a finite lifetime. No oceanic crust survives beyond approximately 200 million years. Everything older has been subducted and destroyed. Consider what this means for preservation. The ocean floor covers approximately 71% of Earth's surface. Any evidence of civilization that existed on this vast area more than 200 million years ago is gone. Not buried deeply where it might someday be excavated. Not transformed but still present. Gone absolutely, melted back into the mantle from which the crust originally formed. Continental crust faces different challenges. It is thicker, typically 30 to 50 kilometers, and less dense than oceanic crust. This buoyancy makes it resistant to subduction. When continental plates collide, rather than one subducting beneath the other, they crumple and thicken, forming mountain ranges. But continents are not permanent structures. They fragment through rifting, where the crust stretches and thins until it breaks completely, creating new ocean basins. They merge through collision, welding together into supercontinents. The cycle of continental assembly and breakup operates on timescales of several 100 million years. During the past billion years, at least 2 full cycles have occurred. The supercontinent Rodinia assembled approximately 1 billion years ago and began to fragment around 750 million years ago. Its fragments eventually reassembled into another supercontinent, Pannotia, around 600 million years ago. Pannotia broke apart, and its fragments later formed Pangaea, which began to assemble 300 million years ago and reached its maximum extent around 250 million years ago. Pangaea then fragmented into the continents we know today. Africa and South America separated, creating the South Atlantic Ocean. India broke away and drifted north, eventually colliding with Asia. Australia separated from Antarctica. North America and Europe split apart, forming the North Atlantic. Each cycle of assembly and breakup dramatically reshapes the continental crust. Mountain ranges form and are eroded away. Sedimentary basins fill with kilometers of sediment, then are uplifted and eroded. Rocks that were once deep in the crust are brought to the surface. Surface rocks are buried to depths where heat and pressure transform them entirely. The oldest continental rocks, dating to 4 billion years ago, are tiny remnants that somehow survived this endless cycle of destruction and recreation. They are zircon crystals, small but nearly indestructible mineral grains that can survive even when the rocks containing them are completely melted and reformed. These zircons tell us that continental crust existed very early in Earth's history, but they tell us almost nothing about what that early crust was like. The rocks themselves are gone, metamorphosed beyond recognition, or eroded away entirely. Only these tiny, resilient crystals remain as witnesses to a world that no longer exists in any other form. If we struggle to find evidence of Earth's early continental crust, despite knowing it existed, what hope is there of finding evidence of civilizations that might have existed on that crust? The rocks that would contain such evidence have been transformed, eroded, subducted. The chemical signatures have been reset by metamorphism. The structures have been destroyed by tectonic forces or weathered away over tens or hundreds of millions of years. Erosion itself deserves particular attention as a mechanism of destruction. On continents, unless actively subsiding, the dominant process is erosion rather than deposition. Rivers carve valleys, carrying sediment to the sea. Glaciers during ice ages scour the landscape, removing vast quantities of rock. Wind abrades exposed surfaces. Chemical weathering dissolves soluble minerals. The rate of erosion varies by location and climate, but a typical figure for continental erosion is approximately 10 to 100 meters per million years. This seems slow, but over 100 million years it represents 1 to 10 kilometers of rock removal. Entire mountain ranges can be completely leveled over such timescales. Any structures or artifacts on an eroding surface would be gradually destroyed. Buildings collapse as their foundations are undermined. Roads are cut by streams. Even massive monuments weather away grain by grain. Eventually, the land surface that once supported a civilization is itself removed, eroded down to deeper and older rock layers. The only way for evidence to be preserved is if it is rapidly buried and remains buried in a subsiding basin, where sedimentation exceeds erosion. But most continental areas are not subsiding. Most are either stable or being uplifted and eroded. The probability that any given location would have the right conditions for preservation is low. The probability that evidence would be both created in such a location and then survive subsequent geological changes is lower still. This is why the fossil record is so incomplete. Despite 4 billion years of life on Earth, we have fossils representing perhaps 1/10 of 1% of all species that ever existed. The incompleteness is not due to lack of searching, but to the fundamental nature of preservation. Most organisms decay completely. Most locations experience erosion rather than deposition. Most sediments, even once formed, are eventually eroded away or transformed beyond recognition. If biological organisms, numbering in the trillions of individuals over millions of years, leave such sparse fossil records, what chance is there that artifacts of civilization created by perhaps millions or billions of individuals over thousands of years, would be preserved and later recognized. The fossil record, what preservation teaches us. The study of fossils provides crucial insights into what can and cannot be preserved across geological time. Paleontology has revealed both the remarkable ability of certain structures to persist for hundreds of millions of years and the profound limitations on what survives. Fossils form through several processes, but the most common is permineralization. When an organism dies and is buried in sediment, its tissues begin to decay, but if burial occurs rapidly before decay is complete, the hard parts, bones and shells and teeth may be preserved. Groundwater percolating through the sediment carries dissolved minerals, typically silica or calcite or iron compounds, which precipitate in the pores and spaces within the bone or shell structure. Over time, the original organic material may be completely replaced, molecule by molecule, with mineral. The result is a fossil that preserves the shape and sometimes even the microscopic structure of the original, but is now composed entirely of rock. This process requires specific conditions. The organism must die in or be transported to an environment where burial occurs. The sediment chemistry must be suitable for mineralization rather than dissolution, and the resulting fossil-bearing rock must survive subsequent geological processes without being eroded away, deeply buried and metamorphosed, or subducted. Each of these requirements eliminates the vast majority of organisms from any possibility of fossilization. Most creatures die in environments where decay is rapid and complete. Most remains are scattered by scavengers or disarticulated by water currents. Most burial occurs in environments where sediment chemistry prevents mineralization or actively dissolves bone. The result is that fossils are extraordinarily rare relative to the number of organisms that have lived. Conservative estimates suggest that between 5 and 50 billion species have existed throughout Earth's history. We have discovered and formally described approximately 300,000 fossil species. This represents, at best, 0.01% of all species that ever existed, and this sparse sample is not random. It is heavily biased towards certain types of organisms and certain environments. Marine organisms with hard shells are vastly overrepresented because shallow marine environments are ideal for fossil formation. Sediment accumulates continuously. Water chemistry often favours preservation. Scavengers are less effective at completely destroying remains underwater. Terrestrial organisms, particularly those living in upland or forested environments, are dramatically underrepresented. These are regions of erosion rather than deposition. Remains are exposed to scavengers, to weathering, to decomposition in oxygen-rich environments. Fossilization is the exception rather than the rule. Insects, despite being extraordinarily abundant and diverse, with more described species than all other animals combined, have an extremely poor fossil record. Their small size and fragile exoskeletons rarely survive the processes necessary for fossilization. Most insect fossils come from exceptional preservation sites where unusual conditions, such as entombment in amber or burial in fine-grained volcanic ash, prevented normal decay. Even among organisms with hard parts living in environments favourable for fossilization, the preservation rate is low. Consider marine bivalves, clams and oysters, which have robust calcite shells and live in shallow seas where sedimentation is active. These are among the most commonly fossilized organisms, yet for every individual bivalve that becomes a fossil, millions live and die without leaving any trace. The implications for detecting ancient civilizations are profound. If organisms specifically adapted for preservation, with mineralized hard parts and living in environments optimal for fossilization, are preserved at rates of perhaps 1 in a million or 1 in 10 million. What rate should we expect for technological artifacts? Stone tools, being already mineralized, might survive burial relatively well. But how would we distinguish an ancient worked stone, millions of years old and possibly altered by metamorphism, from a naturally fractured rock? Without obvious manufacturing marks, without context, a single stone tool would likely be overlooked or dismissed as a geological specimen. Metals present different challenges. Iron oxidizes, reverting to iron oxide, rust, indistinguishable from natural iron ore. Copper and bronze, while more resistant to oxidation, are still subject to corrosion, particularly in acidic environments common in many soils. Even gold, one of the most chemically inert metals, can be dissolved over geological time by certain groundwaters rich in chloride ions or organic acids. Refined metals are thermodynamically unstable at Earth's surface. They represent a state of low entropy, high chemical potential, maintained only by human effort. Once that maintenance ceases, the natural tendency is to revert to lower energy states, oxides, sulfides, carbonates. The metal artifacts of a vanished civilization would gradually transform back into something resembling ore, their artificial origin erased by chemistry. But perhaps some materials might be more stable. Ceramics, fired clay, are already oxidized and relatively inert chemically. Could pottery survive for hundreds of millions of years? In theory, yes. Ceramics are similar to natural rocks in their stability, but they would need to be buried in favourable conditions, protected from mechanical weathering that would fracture and abrade them. And even if fragments survived, would they be recognisable? A pottery shard, after being buried, subjected to pressure from overlying sediments, possibly heated during deep burial, potentially fractured and recemented by minerals from groundwater, might look very similar to a naturally formed clay concretion. Without the context of a vessel shape, without glazes or decoration, without associated artifacts, it might pass unnoticed. Glass presents similar issues. It is chemically similar to certain volcanic rocks. Ancient glass, weathered and altered over millions of years, might be difficult to distinguish from natural volcanic glass or silica concretions without detailed chemical analysis. And such analysis would only be performed if there were reason to suspect the specimen was artificial, creating a circular problem. We need evidence to justify detailed study, but might need detailed study to recognize the evidence. The most durable human artifacts may be the least distinctive. Stone structures, if buried, might survive as jumbled assemblages of rocks. Without obvious symmetry or patterning, without mortar or tool marks, they would likely be interpreted as natural rock formations. The meaning would be lost even if the physical material survived. This is not to say that preservation is impossible. Under extremely favourable conditions, in locations where rapid burial occurred and where subsequent geological history was gentle, evidence might survive, but the conditions necessary are rare. And the probability that we would find and recognise such evidence, even if it existed, is far from certain. The fossil record teaches us humility. It reveals that preservation is the exception, that the vast majority of Earth's history leaves no direct physical evidence, and that what does survive is fragmentary, biased, and often ambiguous in its interpretation. If we struggle to reconstruct the evolution and ecology of organisms that lived for millions of years in enormous populations, how much more difficult would it be to detect civilizations that might have existed for mere thousands of years with populations of millions or billions? The carbon cycle, chemical whispers through time. If physical artifacts are unlikely to survive across hundreds of millions of years, perhaps chemistry might preserve evidence where structure cannot. The behaviour of elements as they cycle through Earth's systems, from atmosphere to ocean to rock and back again, create signatures that can persist when the objects that created them have long since vanished. Carbon, the foundation of organic chemistry, and thus of life itself, moves through the environment in a complex cycle. Plants absorb carbon dioxide from the atmosphere during photosynthesis, converting it into organic compounds. Animals consume plants, incorporating that carbon into their own bodies. Decomposition and respiration return carbon to the atmosphere as carbon dioxide or methane. Some organic material escapes decomposition through burial, eventually forming coal, oil, and natural gas over millions of years. This cycle involves isotopic fractionation. Carbon exists in two stable isotopes, carbon-12 with 6 protons and 6 neutrons, and carbon-13 with 6 protons and 7 neutrons. Carbon-12 is slightly lighter and requires marginally less energy to incorporate into molecules. Plants, therefore, preferentially absorb carbon-12 during photosynthesis, leaving the atmosphere relatively enriched in carbon-13. The result is that organic matter is depleted in carbon-13 compared to the atmosphere or to inorganic carbonates. This depletion is typically about 2 to 3%, small but measurable with modern mass spectrometry. Fossil fuels, being the compressed and altered remains of ancient organic matter, retain this carbon-13 depletion. When fossil fuels are burned, they release carbon dioxide with a distinctive isotopic signature. This altered carbon dioxide is then absorbed into the oceans, where it can be incorporated into the calcium carbonate shells of marine organisms and eventually becomes part of limestone and other carbonate rocks. In theory, a period of intense fossil fuel burning should create a detectable shift in the carbon isotope ratio within a specific layer of sedimentary rock. This shift would appear as a negative excursion, a sudden decrease in carbon-13 relative to carbon-12 preserved in carbonate minerals. This is not merely theoretical. Scientists have detected numerous carbon isotope excursions in the geological record and used them to infer past events. The most dramatic is associated with the Permian-Triassic extinction event, approximately 252 million years ago, which eliminated roughly 90% of marine species and 70% of terrestrial vertebrate species. The carbon isotope record shows a massive negative excursion at this boundary, indicating the release of enormous quantities of carbon-13 depleted carbon. The leading hypothesis attributes this to extensive volcanism in what is now Siberia, which released not only carbon dioxide directly, but also triggered the release of methane from deposits on the ocean floor. This methane, produced by microbial activity, is even more depleted in carbon-13 than terrestrial organic matter, amplifying the isotopic signal. Another example is the Paleocene-Eocene thermal maximum, or PTM, occurring approximately 56 million years ago. Global temperatures rose by 5 to 8 degrees Celsius over just a few thousand years. The carbon isotope record again shows a large negative excursion, suggesting massive release of greenhouse gases. The warming triggered significant extinctions, particularly among deep-sea organisms, and caused dramatic changes in ocean circulation and terrestrial ecosystems. These natural events demonstrate that carbon isotope excursions can be preserved across tens or even hundreds of millions of years. They show that massive releases of carbon-13 depleted carbon leave detectable signatures in the rock record. But they also reveal a critical challenge. How would we distinguish a civilization-caused excursion from a natural one? Both would show similar isotopic shifts. Both would likely be associated with warming and potentially with extinctions. Both would represent geologically rapid events, occurring over thousands to hundreds of thousands of years rather than millions. Without additional evidence, without clear technological signatures accompanying the carbon isotope anomaly, attribution would remain ambiguous. We might look for other markers to help with interpretation. The presence of certain metals in unusual concentrations, for instance. Industrial activity concentrates and redistributes elements in ways that natural processes rarely do. Lead, zinc, copper, cadmium, mercury, all are byproducts of various industrial processes and might appear in elevated concentrations in sediments deposited during a period of industrialization. But here too, ambiguity arises. Volcanic activity releases heavy metals. Hydrothermal vents on the seafloor create metal-rich deposits. Erosion of certain rock types can naturally concentrate metals in sedimentary basins. Without knowing exactly what signature to look for, without having a clear reference example from a confirmed ancient civilization, distinguishing industrial metal pollution from natural metal enrichment requires assumptions that may not be justified. Nitrogen isotopes offer another potential marker. Modern agriculture relies heavily on synthetic fertilizers produced through the Haber-Bosch process, which converts atmospheric nitrogen into ammonia. This process, along with the cultivation of nitrogen-fixing crops, has dramatically altered the nitrogen cycle. The isotopic composition of nitrogen in agricultural runoff differs from natural sources, creating a potentially detectable signature in lake and ocean sediments. But again, natural processes complicate interpretation. The ratio of nitrogen-15 to nitrogen-14 in the environment varies depending on the types of nitrogen-fixing organisms present, on ocean circulation patterns, on rates of denitrification in oxygen-poor waters. Changes in these natural systems can create nitrogen isotope excursions that might be misattributed to agriculture or misinterpreted as purely natural when they were actually anthropogenic. The fundamental challenge is that Earth's geochemical cycles are complex, interconnected, and capable of producing a wide range of signatures through purely natural processes. Volcanism, changes in ocean circulation, variations in biological productivity, erosion patterns all influence the chemical composition of sediments. The signatures we might propose as markers of industrial civilization must be both distinctive enough to stand out against this natural variability and durable enough to survive hundreds of millions of years of diagenesis. The physical and chemical changes that occur during sediment burial and rock formation. Some have suggested looking for the presence of entirely synthetic compounds, molecules that do not occur naturally. Certain plastics, pesticides, pharmaceuticals, industrial chemicals, these are products of human ingenuity with no natural analogues. In theory, their presence in ancient sediments would constitute unambiguous evidence of technological civilization. But these organic compounds are not indefinitely stable. Over geological time, they are subject to breakdown through oxidation, through reactions with minerals in the sediment, through transformation during burial heating. The complex molecular structures of synthetic compounds, the very feature that makes them functional for human purposes, also makes them thermodynamically unstable over millions of years. Plastics might degrade into simpler hydrocarbons indistinguishable from products of organic matter decay. Pesticides might be completely mineralized to carbon dioxide and simpler compounds. Pharmaceuticals might fragment and react until no recognizable structure remains. The timescales involved are so vast that even molecules we consider persistent in human terms become transient when viewed from a geological perspective. There is, however, a more durable class of signatures, changes to the ratios of stable isotopes beyond carbon and nitrogen. Certain industrial processes can alter isotope ratios in ways that natural processes rarely or never achieve. The enrichment of uranium-235 for nuclear fuel or weapons, for instance, necessarily depletes uranium-235 in the waste stream, creating uranium with an anomalous isotopic composition. This altered uranium, if incorporated into minerals, might preserve its anomalous ratio for billions of years. Similarly, the production of pure silicon for electronics involves refining that changes the isotopic composition. The isolation of specific rare earth elements for technological applications creates complementary depletions in source materials. These isotopic anomalies, if present in ancient sediments, would be difficult to explain through natural processes alone. But such anomalies would be localized, present only near the sites of industrial activity. If those sites happened to be in locations that subsequently experienced erosion rather than burial, or if they were located on oceanic crust that has since been subducted, the evidence would be gone. And even if preserved, we would need to analyze the right samples, from the right locations, with the right analytical techniques to detect the anomalies. The chemical record, while potentially more durable than physical artifacts, still faces profound challenges of both preservation and interpretation. It offers tantalizing possibilities, but no guarantees. In the search for ancient civilizations, chemistry provides clues, but rarely proof. Mass extinctions, crisis points in Earth's history. Earth's biological history is punctuated by crises, periods of rapid environmental change during which large percentages of species vanish from the fossil record. These mass extinction events reshape ecosystems, eliminate dominant groups, and create opportunities for survivors to diversify and radiate into emptied niches. 5 major mass extinctions are recognized in the Phanerozoic eon, the past 540 million years. The End-Ordovician extinction, 444 million years ago, eliminated approximately 85% of marine species. The Late Devonian extinctions, occurring in pulses between 375 and 360 million years ago, severely impacted marine life, particularly reef ecosystems. The End-Permian extinction, 252 million years ago, was the most severe, eliminating roughly 96% of marine species and 70% of terrestrial vertebrates. The End-Triassic extinction, 201 million years ago, killed off many large amphibians and enabled dinosaurs to become dominant, and the End-Cretaceous extinction, 66 million years ago, ended the reign of non-avian dinosaurs and many other groups. Each of these events has been studied intensively, and each reveals something about the vulnerability of life to rapid environmental change. The End-Ordovician extinction appears linked to rapid climate change as glaciers formed and then melted on the southern supercontinent of Gondwana, causing sea levels to fall and then rise dramatically. The late Devonian events may relate to the evolution of deep-rooted plants, which enhanced weathering and nutrient runoff, potentially causing oxygen depletion in oceans. The End-Permian extinction, the most severe, likely resulted from multiple causes acting together. Massive volcanism in the Siberian traps released enormous quantities of carbon dioxide and sulfur dioxide, warming the climate and acidifying the oceans. This may have triggered the release of methane from seafloor deposits, further amplifying warming. Ocean circulation weakened, creating widespread anoxia. The combination of warming, acidification, anoxia, and possibly toxic gas release created conditions lethal to most forms of life. The end Triassic extinction coincides with extensive volcanism associated with the breakup of Pangaea and the opening of the Atlantic Ocean. Again, greenhouse gas release and climate change appear to be primary drivers. And the end Cretaceous extinction, famously, was triggered by the impact of an asteroid approximately 10 kilometers in diameter, which struck what is now the Yucatan Peninsula in Mexico. The impact, combined with ongoing volcanism in India, created conditions that eliminated approximately 75% of species. Each extinction event demonstrates that life on Earth is vulnerable to rapid environmental change. Gradual shifts can be accommodated through adaptation and migration, but when changes occur faster than species can evolve or relocate, extinctions result. The rate of change matters as much as the magnitude. Now consider a hypothetical industrial civilization arising millions of years in the past. Such a civilization, burning fossil fuels, releasing greenhouse gases, deforesting landscapes, polluting waters, driving other species to extinction through habitat loss and hunting, would create environmental changes remarkably similar to those we associate with natural mass extinctions. Global temperatures would rise as carbon dioxide and methane accumulated in the atmosphere. Ocean chemistry would shift as the seas absorbed excess carbon dioxide, becoming more acidic. Nutrient runoff from agriculture might create dead zones in coastal waters. The rapid pace of change, occurring over centuries to millennia rather than millions of years, would outpace the ability of many species to adapt. The result would be a mass extinction event visible in the fossil record as a sudden decline in biodiversity. Many species present in older rock layers would be absent from younger ones. The boundary between the two might show evidence of environmental stress, shifts in the types of organisms present, changes in body size, alterations in population structure. But here is the critical question. How would we distinguish such a civilization-caused extinction from the natural mass extinctions we already know occurred? Both would show sudden biodiversity loss. Both would likely be associated with climate change, ocean acidification, and environmental degradation. Both would occur over geologically brief timescales. The end Permian extinction, the most severe in Earth's history, offers an instructive comparison. It unfolded over approximately 60,000 years, an instant in geological time but still 20 times longer than recorded human history. Species diversity collapsed. Global temperatures rose by approximately 10 degrees Celsius. Oceans became acidic and oxygen depleted. The environmental changes were catastrophic and rapid, yet this was caused entirely by natural processes, volcanism and its cascading consequences. No civilization was involved. The Earth proved itself capable of creating conditions as destructive as anything industrial activity might produce, and doing so through purely geological mechanisms. Could we, examining the end Permian extinction with no prior knowledge of its cause, distinguish it from a civilization-induced catastrophe? The answer is uncertain. We would see the environmental changes, the extinctions, the rapid pace of events. We might infer the volcanism from the basalt deposits of the Siberian traps, but if those deposits had been eroded away, if we lacked that physical evidence, would we consider the possibility that the extinction was caused by industrial activity? Probably not. Without independent evidence of civilization, we would search for natural explanations and likely find them satisfactory. Earth's geological processes are varied and powerful enough to explain almost any environmental catastrophe. The assumption that natural causes are responsible is reasonable and generally correct, but this assumption creates a blind spot. If an ancient civilization did cause a mass extinction, we might attribute it to volcanism, to asteroid impact, to changes in ocean circulation, to any of the many natural processes known to trigger extinctions. The signal would be obscured by our expectation that natural processes are the only relevant actors. Some have suggested looking for patterns that might distinguish biological extinctions from other causes. Volcanism-driven extinctions might show geographic patterns, with effects strongest near the volcanic province and diminishing with distance. Asteroid impacts create specific signatures, iridium anomalies, shocked quartz, spherules from vaporized rock. Ocean circulation changes might affect marine species more severely than terrestrial ones. A civilization-caused extinction might show different patterns. If the civilization was global, effects might be globally distributed rather than concentrated near a specific location. If deforestation was a major factor, terrestrial ecosystems might be disproportionately affected. If ocean pollution or fishing were significant, marine extinctions might be severe even as some terrestrial groups survived relatively well. But even these patterns are ambiguous. A large asteroid impact has global effects despite originating at a point. Volcanism, through its atmospheric effects, can cause worldwide climate change. Ocean anoxia can develop globally if circulation weakens. The patterns we might identify as distinctively civilizational could also be produced by certain configurations of natural causes. There is, however, one potential distinguishing feature: the extinction of the civilization itself. Natural mass extinctions are size-selective to varying degrees. The end Cretaceous extinction eliminated large animals preferentially, including all non-avian dinosaurs over 25 kilograms. Smaller organisms, which require less food and can shelter more easily, survived at higher rates. A civilization-caused extinction might show a different pattern. The civilization itself would presumably be among the casualties, either going extinct or declining drastically in population. If that civilization was morphologically distinctive, if its fossils could be recognized as a unique species, then finding that species present before the extinction and absent afterward might be suggestive, particularly if that species was not particularly large or otherwise obviously vulnerable. But this assumes we could identify the civilization species as such. If their morphology was unremarkable, if they were physically similar to related non-technological species, we might not notice the significance of their disappearance, and if they had been effective at preventing their own fossilization through burial practices, or if they lived in environments where fossilization was unlikely, we might have no fossils of them at all. The relationship between mass extinctions and potential ancient civilizations remains deeply ambiguous. Extinctions demonstrate that rapid environmental change is possible and has occurred repeatedly throughout Earth's history. They show that such changes leave detectable signatures that can persist for hundreds of millions of years. But they also show that natural processes alone are fully capable of producing these signatures, making it extraordinarily difficult to infer civilizational causes without additional corroborating evidence. The Anthropocene, our own signature in stone. To understand what evidence a civilization might leave behind, scientists have increasingly focused on the present as an analogue for the deep past. What signature is humanity currently creating in the geological record? What would remain if our civilization ended tomorrow and geologists millions of years hence examined the rocks we are now forming? This inquiry has led to the proposal of a new geological epoch, the Anthropocene, defined by significant human impact on Earth's geology and ecosystems. The term was popularized by atmospheric chemist Paul Crutzen in the year 2000, though the concept has deeper roots in earlier discussions of humanity's environmental effects. The question of when the Anthropocene began is debated. Some argue for the origin of agriculture approximately 12,000 years ago, when humans began significantly altering landscapes through deforestation and cultivation. Others point to the Industrial Revolution beginning in the late 18th century, when fossil fuel combustion began to measurably change atmospheric composition. Still others suggest the mid-20th century, when nuclear testing, plastic production, and other distinctly modern impacts became globally significant. Regardless of its starting date, the Anthropocene is characterized by rapid, global-scale changes to Earth's systems. Atmospheric carbon dioxide levels have risen from approximately 280 parts per million before industrialization to over 420 parts per million today, a rate of increase unprecedented in the past 800,000 years and likely far longer. Global average temperatures have risen approximately 1.1 degrees Celsius since pre-industrial times, with warming accelerating in recent decades. These changes are creating signatures that will be visible in the geological record, assuming preservation occurs. The carbon isotope ratio in carbonate rocks will show a negative excursion reflecting fossil fuel combustion. The presence of synthetic radionuclides from nuclear testing, particularly plutonium-239, will provide an unmistakable marker for the mid-20th century, though these isotopes will decay to undetectable levels within a few 100,000 years. Microplastics, tiny fragments of degraded plastic waste, are now ubiquitous in marine sediments and are being incorporated into sedimentary rocks forming today. These particles, while individual ones will continue to degrade, might collectively form a distinctive layer, a plastic-rich horizon that could be detected millions of years hence if the rocks survive. The extinction rate has accelerated dramatically. Current extinction rates are estimated to be 100 to 1,000 times higher than background rates, approaching levels characteristic of past mass extinctions. If this continues, the Anthropocene will be marked by a significant biodiversity loss, visible in the fossil record as a sudden decline in the number of species present. But here is the critical insight. Despite all these changes, the geological signature of the Anthropocene might be surprisingly subtle when viewed from millions of years in the future. Many of our most impressive structures and artifacts will not survive. Consider our cities. Modern buildings are constructed primarily of steel, concrete and glass. Steel is thermodynamically unstable at Earth's surface, preferring to exist as iron oxide rather than elemental iron. Without continuous maintenance and protection from moisture, steel corrodes, weakening structures until they collapse. Concrete, while more durable, is vulnerable to cracking as water seeps into pores, freezes and expands. Glass weathers and fractures. Within thousands of years, not millions, most buildings would be reduced to rubble. That rubble would then be subject to erosion, grinding it into smaller and smaller fragments. Eventually, individual bricks, or concrete chunks, abraded and weathered, might become indistinguishable from natural rock fragments. Roads would fare similarly. Asphalt degrades in sunlight and through oxidation. Concrete roads crack and fragment. Within tens of thousands of years, most road systems would be obliterated, particularly in regions experiencing active erosion. Large monuments and structures might survive longer. The Great Pyramids of Giza, constructed of limestone blocks weighing up to 80 tons each, might persist for hundreds of thousands of years in Egypt's dry climate. But even these would eventually succumb to erosion, and if climate changed, if Egypt became wetter or experienced glaciation, the rate of destruction would accelerate dramatically. Underground structures might have better preservation potential if they happened to be in subsiding basins where burial occurred. Tunnels, subways, sewers, these could potentially fill with sediment and be preserved as anomalous voids or sediment-filled structures. But distinguishing them from natural caves or erosional features might be challenging without obvious artificial features like walls or remains of construction materials. The artifacts that stand the best chance of preservation are those already geological in nature. Stone tools, ceramic pottery, glass objects, these are chemically stable and might survive if buried. But individual artifacts, even if preserved, might be difficult to recognize without context. A single stone tool, weathered and possibly altered by heat and pressure during burial, might be dismissed as a naturally fractured rock. A pottery shard, fractured and recemented by mineral precipitation, might resemble a natural concretion. What about metal artifacts? gold jewellery, platinum components from industrial processes, titanium implants from medical devices, these metals are more resistant to corrosion than iron or copper. But they would still be subject to chemical weathering over millions of years, and even if preserved, individual small objects buried in sediment would be extraordinarily unlikely to be found without extensive searching. The most durable signature might not be artifacts at all, but rather the chemical and isotopic changes we have created. The carbon isotope excursion from fossil fuel burning will persist in carbonate rocks. The extinction event we are causing will be visible in the fossil record. The presence of certain synthetic compounds and altered element concentrations in sediments might be detectable, though interpreting these signatures as technological rather than natural would require assumptions that might not be justified without additional evidence. There is also the possibility of a unique marker: radioactive waste from nuclear power and weapons. High-level nuclear waste contains isotopes with half-lives ranging from thousands to millions of years. If this waste is stored in deep geological repositories as planned, it could potentially be detected far into the future. The presence of concentrated fission products in unusual isotopic ratios would be difficult to explain through natural processes. But again, this assumes the repository remains intact and undisturbed. Tectonic activity, erosion, glaciation, all could destroy or disperse the waste, and the volumes are relatively small, concentrated in specific locations. Finding these deposits millions of years hence would require searching in the right places, perhaps an unlikely scenario without some indication of where to look. The Anthropocene, examined as a case study, reveals both promise and limitation. We are creating signatures that will persist, but many of them are subtle, ambiguous, or localized. Our physical structures, which seem so permanent and impressive on human timescales, are ephemeral when viewed from geological perspectives. The most lasting evidence of our existence may be the environmental changes we have caused and the extinction event we are contributing to, but these signatures closely resemble those created by natural catastrophes. If future geologists belonging to some post-human species or visiting from another world examined Earth's rocks millions of years after humanity's disappearance, would they recognize that an industrial civilization had existed? Perhaps, if they knew what to look for, if they sampled extensively, if preservation was favorable. But perhaps not. The signatures might be too subtle, too localized, too ambiguous to be confidently attributed to civilization, rather than to some unusual confluence of natural processes. And if our own signatures might be missed despite our global presence and technological sophistication, how much more easily might earlier civilizations have vanished without a trace? Deep time and human cognition, the struggle to comprehend. One of the fundamental challenges in contemplating ancient civilizations is not merely the geological difficulty of preservation and detection, but the psychological difficulty of truly grasping deep time. Human cognition evolved to deal with timescales of immediate relevance: days, seasons, years, perhaps decades. We can intellectually understand longer periods, but intuitive comprehension breaks down when we venture into thousands, millions, or billions of years. Consider the age of Earth, 4.54 billion years. This number is easy to write, but what does it mean? How do we conceptualize such a span? One approach is to use scaling. If Earth's history were compressed into a single calendar year, with the planet forming at midnight on January 1st, then the first life appears around late February. Complex multicellular organisms emerge in mid-November. the Cambrian explosion occurs around November 18th. Dinosaurs appear on December 13th and go extinct on December 26th. Modern humans emerge at approximately 11:58 p.m. on December 31st. All of recorded history occupies the final 10 seconds before midnight. This scaling helps, but it also obscures. When we compress billions of years into a single year, we lose the sense of the immensity within each period. The age of dinosaurs was not a single era, but rather 165 million years of continuous evolution, climate change, continental drift, during which thousands of dinosaur species arose and went extinct, most having no temporal overlap with one another. Tyrannosaurus rex lived approximately 66 million years ago. Stegosaurus lived approximately 150 million years ago. The temporal gap between Stegosaurus and T-Rex is greater than the gap between T-Rex and the present day, yet we group them together as dinosaurs and imagine them as contemporaries, collapsing 84 million years of history into a single mental category. This cognitive compression makes it difficult to grasp the opportunities deep time provides. When we consider whether an ancient civilization might have existed, we tend to imagine a specific period, a particular time and place. But we are considering not a moment, but an expanse of hundreds of millions of years, during which Earth's surface was completely remade multiple times. During the Phanerozoic eon alone, the past 540 million years, there have been approximately 50 million generations of complex organisms, each facing environmental pressures, each adapting or going extinct. Intelligence, at least of the kind we recognize in ourselves, appeared once in the lineage leading to humans. But 50 million generations represent 50 million opportunities for evolution to explore different paths, different solutions to survival challenges. The probability of any specific outcome, such as human-level intelligence, might be extraordinarily low, but multiplied across 50 million trials, even very low probabilities become less dismissible. And we must remember that the Phanerozoic represents only the most recent 12% of Earth's history. Complex life existed for tens of millions of years before the Cambrian. Simple life existed for billions of years before that. The sheer vastness of time means that rare events become inevitable. Asteroid impacts, supervolcano eruptions, rapid climate shifts, all have occurred repeatedly. The improbable becomes probable, the unlikely becomes certain, given sufficient time. Could intelligence and civilization be among those rare but recurring events? Human psychology resists this possibility, and the resistance is revealing. We have a strong intuitive sense that we are special, unique, the culmination of evolution. This belief is reinforced by the fact that no other species on Earth currently possesses our cognitive capabilities. We are the only species to have developed language, abstract reasoning, cumulative culture, technology, but this uniqueness might be historical contingency rather than evolutionary inevitability. We know that intelligence has evolved multiple times independently. Cephalopods like octopuses and cuttlefish possess remarkable cognitive abilities, despite having evolved from molluscan ancestors completely independently of vertebrates. Corvids, particularly crows and ravens, demonstrate problem-solving abilities comparable to great apes. Parrots show understanding of abstract concepts like zero and numerical counting. Intelligence is not a single trait, but a collection of capacities that can evolve separately and recombine in various ways. Tool use has evolved in multiple lineages. Social cooperation has evolved countless times. Problem-solving, memory, communication all have analogues throughout the animal kingdom. What humans possess is a specific combination of these traits developed to a particular degree, but the individual components are not unique to our lineage. Given this, and given the vastness of time, it seems at least possible that other combinations, other configurations of cognitive capacity might have arisen in earlier periods. They might not have been human in any sense, might have had completely different sensory systems, different forms of communication, different approaches to manipulating their environment. But they might nonetheless have developed what we would recognize as intelligence and perhaps technology. Our inability to find evidence of such civilizations might reflect not their non-existence, but rather the limitations of preservation, the brevity of their existence compared to geological timescales, and our own cognitive biases about what intelligence looks like and how it should manifest in the fossil record. There is also the challenge of recognizing what we do not expect. Human paleontology and archaeology are guided by theories about what ancient humans and their ancestors should look like, where they should be found, what artifacts they should have created. These theories allow researchers to distinguish human fossils from those of other animals, to recognize stone tools as artificial rather than natural. But if we encountered fossils or artifacts from a non-human civilization, would we recognize them? If the biology was different, if the technology was based on different principles, if the civilization arose in an environment where preservation was poor, we might overlook the evidence even if we found it. This is not idle speculation. History provides examples of evidence being overlooked because it did not fit expectations. The first dinosaur fossils were not recognized as representing a distinct group of extinct reptiles until comparative anatomy had developed sufficiently to place them in context. Before then, fossil bones were often attributed to giant humans, to dragons, to extinct elephants. Neanderthal fossils, first discovered in the 19th century, were initially misinterpreted as pathological modern humans or as representing a separate primitive lineage unrelated to our ancestry. Only gradually did scientists recognize Neanderthals as close relatives with whom modern humans interbred. If evidence of ancient civilizations exists, it might be sitting in museum collections classified as something else, or lying undiscovered in rock formations not considered relevant to the search for technological intelligence. We find what we look for, and we rarely look for what we do not expect to find. Deep time, combined with the limits of human cognition and the biases inherent in scientific inquiry, creates a space of profound uncertainty. We cannot prove that ancient civilizations existed, but neither can we confidently assert they did not. The question remains open, residing in the vast grey area between what we know and what we can know given the constraints of geology, preservation, and time itself. Alternative intelligences. What might cognition look like? When we contemplate the possibility of ancient civilizations, we tend to imagine them as essentially human-like, bipedal, tool-using, verbal, with social structures and technologies recognizable as variations on our own. But intelligence and civilization, if they arose independently in different lineages, might take forms radically different from anything in human experience. Consider the octopus. This creature evolved from molluscan ancestors that diverged from the vertebrate lineage approximately 600 million years ago. Octopuses have large brains, complex behaviors, and problem-solving abilities that rival those of mammals. They can navigate mazes, open containers, use tools, recognize individual humans, and even engage in what appears to be play. But octopus intelligence is profoundly alien in its structure. Their nervous system is distributed. Approximately 2/3 of their neurons are in their arms rather than their central brain. Each arm has considerable autonomy, capable of complex behaviours without direct central control. An octopus might simultaneously be exploring with one arm, manipulating an object with another, and defending itself with a third, with minimal central coordination. Their sensory world is equally alien. Octopuses see polarized light, a dimension of visual information invisible to humans. Their skin contains light-sensitive proteins, meaning they can essentially see with their entire body, detecting changes in lighting and possibly even patterns without using their eyes. Their sense of touch is highly developed, with arms capable of detecting chemical cues, texture, and shape through contact. Communication, when it occurs, is primarily visual. Octopuses change colour and pattern rapidly using specialised cells in their skin called chromatophores, iridophores, and leucophores. These displays can signal aggression, courtship, camouflage, or possibly more complex information. But they are fundamentally different from human language, which is sequential, symbolic, and arbitrary in its relationship between signifier and signified. Could a species like this, given different environmental pressures and evolutionary history, develop civilization? The conventional answer is no, primarily because octopuses are solitary, short-lived, and lack cumulative culture. Individual learning dies with the individual. Each generation starts essentially from scratch. But these are features of current octopuses, shaped by their particular evolutionary history. A different branch of cephalopod evolution, facing different selection pressures, might have evolved social structures, extended lifespans, and mechanisms for transmitting information across generations. The fundamental cognitive capacity is present. What is lacking is the specific configuration of life history traits that would favour civilization. Corvids, particularly crows and ravens, offer another example of alternative intelligence. These birds demonstrate understanding of cause and effect, can plan for the future, use tools in novel ways, and recognise individual humans even after years of separation. They engage in what appears to be deception, hiding food from other corvids and later moving it if they suspect they were watched during the initial hiding. Their intelligence operates within a brain that is tiny compared to mammalian brains, but organised very differently. Whereas mammalian intelligence relies heavily on the neocortex, a layered structure on the brain's outer surface, avian intelligence is mediated by structures like the pallium, organised in clusters rather than layers. This architecture is convergently evolved, achieving similar computational capabilities through completely different neural organisation. Social transmission of information occurs in corvids. Crows can learn to recognise dangerous humans from other crows, even if they never personally had a negative encounter. They appear to hold grudges, responding negatively to specific individuals for years. In some populations, crows have been observed using traffic to crack nuts, placing them on roads and waiting for cars to run over them, then retrieving the contents when traffic clears. This behaviour is remarkable because it demonstrates not just tool use, which is common in corvids, but tool use involving human technology in ways that were certainly not instinctual. It was learned, refined, and transmitted culturally within crow populations. It shows a capacity for innovation and cultural evolution. Could a corvid lineage, given different circumstances, develop civilization? Again, the conventional answer is no. Limited by factors like lack of manipulative appendages, wings are not suitable for fine manipulation, and energy constraints, flight is metabolically expensive, limiting brain size. But evolution is opportunistic. If selection favoured increased intelligence and tool use, modifications might evolve, reduction in flight capability in exchange for larger brains and more versatile forelimbs, as occurred in some extinct bird lineages. These examples illustrate that intelligence is not confined to a single body plan or neural architecture. It has evolved multiple times through different pathways, resulting in different but nonetheless effective cognitive systems. If we encountered evidence of an ancient non-human civilization, its technology and artifacts might not resemble ours at all. A civilization of marine organisms might create structures from coral, shell, or secreted minerals rather than smelted metals. Their technology might be primarily biological, using selectively bred organisms to perform tasks rather than constructing mechanical devices. Their communication might be acoustic, using complex sounds in water, or chemical, using scent trails and pheromones. A civilization that evolved in environments without abundant surface metals might never develop metallurgy as we understand it. Instead, they might master ceramics, glass, and biological materials. Their architecture might be based on grown structures, carefully cultivated organisms shaped into desired forms, rather than assembled buildings. Would we recognize such a civilization if we encountered its remains? A coral structure, even if deliberately shaped and placed, might be interpreted as natural. Ceramics, weathered and fragmented over millions of years, might be dismissed as concretions or unusual mineral formations. Biological technologies would leave almost no trace, degrading completely within years or decades of abandonment. The more different an ancient civilization was from our own, the less likely we would be to recognize its evidence. Our search methods, our interpretive frameworks, are all calibrated to find things like us. We look for stone tools because we made stone tools. We look for hearths and buildings because we used fire and built structures. We look for metal artifacts because we developed metallurgy. An intelligence that followed a completely different technological pathway might be invisible to our searches, not because it left no trace, but because its traces do not match our expectations of what technological civilization looks like. This possibility profoundly complicates the question of ancient civilizations. It suggests that even if we have thoroughly searched the geological record for evidence of technological intelligence, we might have found that evidence but not recognized it. The stones dismissed as natural might be tools from a non-human technology. The unusual mineral formations might be remnants of structures we cannot conceptualize. The chemical anomalies attributed to volcanism might actually reflect industrial processes operating on principles we have never discovered. We are searching for ourselves in the past, looking for the specific signatures that our kind of civilization creates. But if intelligence and civilization are more diverse, more varied in their manifestations than we have imagined, then the search becomes vastly more difficult. We might be surrounded by evidence we cannot interpret, clues we cannot recognize, messages written in languages we do not know exist. The pace of evolution, timescales for intelligence. If we accept that ancient civilizations are theoretically possible, given sufficient time and the right circumstances, we must then ask, how long does it take for intelligence to evolve? And how often might conditions be right for that evolution to proceed towards civilization? The evolutionary history of intelligence on Earth provides some constraints, though these must be interpreted carefully. Complex nervous systems evolved relatively early in animal history. By the Cambrian period, 540 million years ago, arthropods possess sophisticated compound eyes and behaviours suggesting substantial neural processing. Vertebrates, also present in the Cambrian, had developed centralised nervous systems with distinct brains. But complexity of nervous system does not directly equate to intelligence as we typically define it. Many organisms with large, complex nervous systems demonstrate primarily reflexive or instinctual behaviours. Intelligence, in the sense of flexible problem-solving, learning and behavioural innovation, appears to require not just neural complexity, but specific types of neural organisation and specific environmental pressures favouring cognitive flexibility over stereotyped responses. Among vertebrates, intelligence has evolved to high degrees independently in multiple lineages. Primates, including humans, are one obvious example. Cetaceans, whales, and dolphins possess large, complex brains and demonstrate sophisticated social behaviours, communication, and apparent self-awareness. Elephants show remarkable memory, social complexity, and innovative problem-solving. Corvids, as previously discussed, demonstrate intelligence comparable to primates despite completely different brain architecture. Among invertebrates, cephalopods stand out for cognitive abilities far beyond what is typical for mollusks. Their intelligence evolved independently, driven by predation pressures and the complex spatial environments of coral reefs and rocky coastlines. These independent evolutions of intelligence suggest that the capacity can arise relatively readily, given appropriate selection pressures. But they also reveal that high intelligence is not inevitable. The vast majority of animal lineages have not evolved cognitive abilities approaching those of primates or cetaceans. For every intelligent species, there are thousands that survive perfectly well with minimal cognitive flexibility, relying instead on instinct, rapid reproduction, or other strategies. What conditions favour the evolution of intelligence? Several factors appear important. Complex social environments create selection pressure for understanding and predicting the behaviour of conspecifics, leading to the evolution of social cognition. Variable or unpredictable physical environments favour behavioural flexibility over fixed responses, creating pressure for learning and innovation. Predation, both avoiding predators and capturing evasive prey, favours cognitive abilities that enable planning, deception, and novel strategies. Tool use, while often associated with intelligence, is not clearly a cause or an effect. Some highly intelligent species rarely use tools. Some species with modest cognitive abilities use tools regularly in stereotyped ways. Tool use might amplify selection for intelligence by creating situations where problem-solving provides clear fitness benefits, but it is not strictly necessary. The transition from high intelligence to technological civilization involves additional steps. Anatomical factors matter. Manipulative appendages capable of fine control enable the creation and use of complex tools. Terrestrial environments provide advantages over aquatic ones. Fire is not possible underwater, and many materials and chemical processes are difficult or impossible in aquatic environments. Social structure is critical. Cumulative culture, the ability to transmit knowledge across generations and build upon it incrementally, requires social learning mechanisms, longevity sufficient to allow teaching and learning, and population sizes and structures that maintain information over time. Humans possess all of these features, but they are not uniquely human. Some cetacean populations show evidence of cumulative culture, as do some primate groups and even some bird species. Environmental stability also matters, though in subtle ways. Too stable, and there is little pressure for innovation. too unstable, and populations cannot grow or persist long enough to develop complex culture. An intermediate level of environmental variability, with challenges that are difficult but not impossible to overcome, seems optimal for the evolution of behavioral and technological complexity. Given these requirements, how often might technological civilization arise? On Earth, it has occurred once in approximately 4 billion years of life and 540 million years of complex multicellular organisms. This suggests either that the conditions are extraordinarily rare or that the evolutionary pathway is highly contingent, dependent on specific sequences of events unlikely to be repeated. But we have only one example, one planet, one history to examine. Statisticians would caution strongly against drawing confident conclusions from a sample size of one. The fact that technological civilization arose once tells us it is possible, but it tells us almost nothing about the probability. If we assume conservatively that technological civilization can arise at most once in the history of a planet, then Earth's example suggests no ancient civilizations could have existed before humans, but this assumption has no theoretical justification. There is no known principle of biology or evolution that would prevent intelligence and civilization from arising multiple times, given sufficient opportunities and sufficient time for evolution to explore different pathways after previous intelligent species went extinct. Consider an alternative scenario. Suppose that technological civilization arises on average once every 500 million years on a habitable planet. This is a low probability. During 500 million years, thousands of mammal species, tens of thousands of bird species, millions of insect species might evolve and go extinct. Intelligence leading to civilization would be occurring in a tiny fraction of 1% of lineages, an exceedingly rare outcome. Yet if this were the rate, Earth's 4 billion year history of life would have had time for approximately 8 such civilizations to arise independently. Most would leave no detectable trace, erased by geological processes. The few that left traces might be ambiguous, attributable to natural processes without the context necessary to recognize their artificial origin. This is speculative, of course. We have no empirical basis for estimating the rate at which technological civilization emerges, but the speculation illustrates that even with very conservative assumptions about probability, deep time provides enough opportunities that multiple instances become plausible. Moreover, we must remember that extinction is not uniformly catastrophic across all species. When an extinction event occurs, some lineages disappear entirely while others survive and diversify to fill the emptied niches. If an intelligent technological species went extinct, perhaps due to environmental changes it created or failed to mitigate, other lineages would survive and evolution would continue. Given tens of millions of years, those surviving lineages would diversify and adapt. Some might evolve toward intelligence again, driven by selection pressures similar to those that favored intelligence previously. The ecological role of intelligent problem solver is not unique to humans. If we vanished, would another lineage eventually fill that niche? Given sufficient time, quite possibly yes. This cycle could potentially repeat multiple times over Earth's history. Intelligence evolves, civilization develops, environmental stress or other factors lead to collapse and possibly extinction. Other lineages survive and diversify. Intelligence evolves again in a different lineage. Each iteration would leave minimal traces, gaps of millions of years between them would erase most evidence, and the specific biological forms would be completely different each time. From our current vantage point, examining a fragmentary geological record and biased toward recognizing only intelligence that resembles our own, we might find no convincing evidence. Yet the events could have occurred nonetheless, hidden not by active concealment, but by the simple passage of deep time and the limits of preservation, ocean worlds and the marine barrier. Much of our discussion has implicitly assumed terrestrial civilizations, species living on land and developing technology in air, but Earth's surface is predominantly ocean, covering approximately 71% of the planet. For most of Earth's history, marine environments were more biologically productive and diverse than terrestrial ones. Could an intelligent species evolve in the ocean and develop what we would recognize as civilization? The question is complicated by the fundamental differences between aquatic and terrestrial environments. Many of the materials and processes central to human technology are difficult or impossible in water. Fire cannot exist underwater, eliminating the most accessible form of energy transformation and heat generation that enabled human metallurgy, ceramics, and eventually engines. Metals in their pure, reduced forms are not stable underwater. Iron oxidizes rapidly, forming rust. Copper corrodes. Even relatively inert metals like gold can be slowly dissolved by seawater, rich in chloride ions over geological time. This does not mean marine organisms could not use metals, but it means the availability and stability of metallic materials is profoundly different in aquatic environments. The transmission of light is limited underwater. Even in the clearest ocean water, sunlight penetrates only to depths of a few hundred meters. Below this, permanent darkness prevails, illuminated only by bioluminescence produced by organisms themselves. Visual communication and visual navigation, central to human culture and technology, would be limited or unavailable in deep ocean environments. Sound, conversely, travels much better in water than in air. The speed of sound in seawater is approximately 1,500 meters per second, more than 4 times faster than in air, and sound attenuates less rapidly, allowing communication over vast distances. Cetaceans use this property extensively, with some whale species communicating across entire ocean basins. An intelligent marine species might develop a sophisticated acoustic culture, far more complex than human spoken language. Sound in water can convey not just simple signals but rich, multi-dimensional information. Frequency, amplitude, duration, directionality, echo patterns, all can be modulated and combined to transmit complex information. Dolphins use echolocation with such precision that they can distinguish between different types of metal underwater, suggesting a form of perception alien to terrestrial experience. But sound, while excellent for communication and navigation, is less useful for manipulating the physical environment. A marine civilization might develop biological technologies, selectively breeding organisms to perform specific tasks, much as humans domesticated plants and animals but taken to far greater sophistication. Coral could be cultivated into structures, sponges selected for particular filtering properties, bioluminescent organisms used for illumination, venomous species employed for defense or hunting. Such technologies would leave minimal fossil evidence. Living structures decay upon abandonment. Biological innovations cannot be distinguished from natural evolution. The entire technological base of an advanced marine civilization might be fundamentally invisible in the geological record, leaving only perhaps chemical signatures from waste products or population concentrations, and these would be ambiguous, easily attributed to natural biological processes. Temperature control presents another challenge in aquatic environments. Water has a high heat capacity, meaning it requires substantial energy to change its temperature. In terrestrial environments, fire provides concentrated heat capable of melting metals, firing ceramics, and driving chemical reactions. Underwater, achieving similar temperatures would require either locating natural hydrothermal vents, which occur only in specific geological settings, or developing alternative energy sources. Electricity is theoretically accessible. Many aquatic organisms, from electric eels to sharks, have evolved biological electrical generation and sensing. A marine civilization might develop this capacity to greater degrees, using bioelectric fields for communication, sensing, or even energy transfer. But generating and controlling electricity on the scales necessary for industrial processes would be challenging in the conductive environment of seawater. The question then becomes whether any marine species on Earth has shown the cognitive capacity that might lead toward civilization, given different evolutionary pressures or different environmental circumstances. Cetaceans are the obvious candidates. Whales and dolphins possess large brains with complex folding and substantial neural density. Sperm whales have the largest brains of any animal, averaging 8 kilograms, compared to approximately 1.4 kilograms for humans. The neocortex, the region associated with higher cognition in mammals, is highly developed in cetaceans, though organized differently than in primates. Cetacean behavior suggests substantial intelligence. They demonstrate social learning, with different pods of killer whales exhibiting distinct hunting techniques passed down through generations. They show signs of self-awareness, passing mirror tests that indicate recognition of self as distinct from others. Their communication involves complex vocalizations, and there is evidence of regional dialects, suggesting cultural variation. Humpback whales produce complex songs that change over time, with innovation spreading through populations. The purpose of these songs is not entirely understood, but they represent one of the most sophisticated non-human vocalizations known, with hierarchical structure and variations that suggest they may convey complex information. Dolphins engage in behaviors suggesting teaching and learning. Mothers have been observed instructing their young in specific techniques, such as using sponges to protect their rostrums while foraging on the seafloor. This behavior is not instinctual, but learned and transmitted culturally, present in some populations but not others despite similar environments. Yet despite this cognitive sophistication, cetaceans have not developed technology beyond the simplest tool use. This is often attributed to anatomical constraints. Flippers are excellent for swimming, but poor for manipulation, lacking the flexibility and opposition necessary for creating and using complex tools. Without the ability to manipulate the environment, cognitive capacity cannot easily translate into technology. But this limitation is not absolute. Evolution could potentially modify cetacean anatomy given appropriate selection pressures. Some extinct cetaceans had different body plans with less specialized flippers, a lineage that faced selection favoring increased manipulation, perhaps in environments with abundant food sources that required processing or complex strategies to access, might evolve more versatile appendages even at some cost to swimming efficiency. Cephalopods, particularly octopuses, have already been discussed as possessing remarkable intelligence despite their phylogenetic distance from vertebrates. Their 8 flexible arms are capable of precise manipulation, able to open containers, manipulate objects, and explore complex 3-dimensional spaces. An octopus can operate in ways that would be impossible for a creature with rigid limbs. But octopuses face different constraints. Most species are solitary, with no social structures to facilitate cultural transmission. They are short-lived, typically living only 1 to 5 years, providing little time for individual learning and no opportunity for extended teaching of young. Most species engage in seminal parity, reproducing once at the end of life and dying shortly thereafter, meaning parents never interact with their offspring. These life history traits make cumulative culture nearly impossible. Each individual must learn largely on its own, and innovations die with the innovator. But again, these are features of extant octopuses, not necessary features of all cephalopod evolution. A lineage facing different selection pressures might evolve longer lifespans, might develop social structures, might shift toward extended parental care. If such a lineage arose, flourished for some period, and then went extinct, what traces might remain? Their soft bodies would rarely fossilize. Any structures or tools they created from biological materials would decay completely within years or decades of abandonment. Chemical signatures from waste or metabolism might be present in ancient sediments, but attributing these to intelligent activity rather than natural biological processes would be nearly impossible without additional context. The ocean presents challenges for the evolution of technological civilization, challenges that may explain why no marine species on Earth has developed such capabilities. But the challenges are not absolute barriers. They are differences in constraints that would shape technology in different directions than the terrestrial path humans followed. A marine civilization, if it existed, would be harder to detect than a terrestrial one. Its technologies would be less durable, its structures more ephemeral, its impact on the chemical environment more easily confused with natural biological processes. The absence of evidence for marine civilizations in the geological record tells us relatively little about whether such civilizations might have existed, because we would not expect to find clear evidence even if they had. The energy question: power sources for civilization. Central to any technological civilization is access to energy. The ability to perform work, to transform materials, to overcome natural constraints, all require energy inputs beyond what biological metabolism alone can provide. For human civilization, this energy has come from a sequence of sources, each enabling new capabilities and new levels of complexity. Initially, human energy was limited to muscle power, both human and animal. Draft animals like oxen and horses multiplied the work that could be accomplished, enabling agriculture on larger scales, the transport of heavy goods, and construction of substantial structures. Wind and water power, captured through sails and mills, provided mechanical energy for grinding grain, sawing wood, and later powering early machinery. But the transformation to industrial civilization came with the exploitation of fossil fuels. Coal, abundant and energy-dense, could produce heat far exceeding what wood could provide, enabling metallurgy on industrial scales. The steam engine, powered by coal, converted heat into mechanical work with efficiencies previously unattainable, driving factories and locomotives and ships. Oil and natural gas, more energy-dense and easier to transport than coal, enabled further expansion. Internal combustion engines revolutionized transportation. Power plants generated electricity, allowing energy to be distributed widely and used in countless applications. The petrochemical industry created materials and chemicals impossible to produce otherwise. This progression raises a critical question about ancient civilizations. What energy sources would they have used? Fossil fuels, which enabled human industrialization, are themselves products of biological processes operating over millions of years. Coal formed primarily from plant material buried during the Carboniferous period, 300 to 350 million years ago, when vast forests were growing on land that later subsided and was covered by sediment. Before the evolution of lignin-degrading fungi, plant material buried in swamps did not fully decay, allowing carbon to accumulate in thick deposits. These deposits, subjected to heat and pressure during burial, transformed into peat, then lignite, then bituminous coal, and finally anthracite, depending on the degree of metamorphism. Oil and natural gas formed primarily from marine microorganisms, plankton and algae, that lived in ancient seas. When these organisms died, they sank to the seafloor. In environments where oxygen was limited and burial was rapid, the organic matter was not fully oxidized but instead was preserved in sediments. Over millions of years, heat and pressure transformed this organic material into kerogen, then into oil and gas, which migrated through porous rocks until trapped by impermeable layers. The formation of fossil fuels is contingent on specific conditions: abundant organic production, rapid burial, limited oxygen, appropriate heat and pressure over millions of years. These conditions have not been continuously present throughout Earth's history. Coal deposits are particularly concentrated in certain periods, notably the Carboniferous and Permian for the oldest coals, and the Cretaceous for younger ones. Oil source rocks are similarly concentrated in certain periods when oceanic conditions favoured the preservation of organic matter. An ancient civilization arising before the Carboniferous, or during a period when organic material was being efficiently recycled rather than buried, would have had limited or no access to fossil fuels. What energy sources might they have used instead? Biological energy, the burning of wood or other organic materials, would always be available but provides only limited energy density. It is sufficient for cooking, heating, and simple metallurgy, working with low melting point metals like copper. But it is insufficient for industrial scale processes requiring sustained high temperatures. Hydroelectric power is theoretically available wherever there is flowing water and the technological capability to construct dams and water wheels. But early hydroelectric utilization requires materials capable of withstanding water pressure and mechanical stress, and these are not available without first developing metallurgy or advanced ceramics. Wind power similarly requires sophisticated materials and engineering. Sails can be made from plant fibers, and simple windmills from wood, but efficient wind power generation requires understanding of aerodynamics and materials science that typically comes after initial industrialization. Geothermal energy, heat from Earth's interior, is locally available near volcanic regions and hydrothermal fields. A civilization developing in such an environment might exploit this energy source without needing fossil fuels. Geothermal heat could drive steam engines, provide high temperatures for metallurgy, and power various industrial processes. The challenge is that geothermal resources are geographically limited, concentrated in tectonically active regions. Solar energy is abundant but diffuse. Concentrating solar heat to useful temperatures requires mirrors or lenses, which in turn require either glass or highly polished metals. These materials are not easily produced without already having high temperature capabilities, creating something of a technological catch-22. Nuclear energy, either fission or fusion, requires extraordinarily sophisticated technology, an understanding of physics that typically comes very late in a civilization's development. It seems unlikely that a civilization could develop nuclear power before first mastering fossil fuels or other energy sources, though it is not strictly impossible. The availability of energy thus constrains the possible paths for technological development. A civilization without access to fossil fuels might develop differently, perhaps remaining at a pre-industrial or early industrial level for much longer. Such a civilization would still be intelligent, still possess culture and technology, but might not create the kinds of energy-intensive processes and materials that produce clear geological signatures. Alternatively, a civilization might discover unusual energy sources that we have not considered. Certain chemical reactions release substantial energy without requiring high initial temperatures. Thermite, a mixture of aluminum powder and metal oxide, burns at extremely high temperatures once ignited, sufficient for welding and metal cutting. A civilization that discovered such exothermic reactions might use them where we would use fossil fuels. Biological energy storage and release might be developed to greater efficiency than anything in nature. Organisms like electric eels store energy in specialized organs and release it in powerful discharges. Imagine this capability enhanced and controlled, living batteries producing electricity from metabolic processes. Such biotechnology would require sophisticated understanding of biology, but might be achievable without first developing fossil fuel-based industry. The diversity of possible energy pathways suggests that civilizations might develop along trajectories quite different from humanity's. Some of these pathways might leave recognizable signatures in the geological record, evidence of geothermal exploitation, chemical residues from industrial processes, altered isotope ratios from particular energy-intensive reactions. But others might be nearly invisible, particularly if they relied primarily on biological or renewable resources that leave minimal permanent traces. The question of energy also affects the duration and sustainability of civilizations. Fossil fuels are non-renewable on relevant timescales. A civilization that depended heavily on them, as humans currently do, would face eventual depletion. This might force a transition to renewable sources, limit the duration of the high-energy industrial phase, or lead to collapse if the transition failed. A civilization powered by renewable or biological sources from the beginning might be more sustainable but less energetically intensive. Its technological capabilities might be more limited, its population smaller, its environmental impact subtler. Such a civilization could potentially persist for much longer than a fossil fuel-dependent one, but it would also be harder to detect in the geological record because it would create fewer dramatic signatures. These considerations add another layer of uncertainty to the question of ancient civilizations. We're searching for signatures similar to those produced by our own fossil fuel-powered industrial society. But if ancient civilizations followed different energy pathways, they might have produced entirely different signatures, ones we are not looking for and might not recognize if we encountered them. Bioengineering as alternative technology. In contemplating possible ancient civilizations, we have largely focused on inorganic technology, tools made from stone and metal, structures built from rock and ceramic, energy from fire and fuel. But this focus reflects our own technological history and biases. Another path exists, one that uses biological systems as the primary technology platform. Life is extraordinarily sophisticated in its material science. Spider silk, gram for gram, is stronger than steel and tougher than Kevlar. Nacre, the iridescent material in abalone shells, is composed of microscopic calcium carbonate plates held together by organic polymers, creating a composite material twice as tough as advanced ceramics. Diatoms, microscopic algae, construct intricate shells of silica glass with features measured in nanometers, achieving through biological processes what human technology can barely replicate. Organisms produce materials under ambient conditions, in water at room temperature, using only the resources available in their environment. They construct complex three-dimensional structures with precision that exceeds most human manufacturing. They self-repair when damaged and adapt to changing conditions. They are in essence already sophisticated nanotechnology, operating at molecular scales with exquisite control. A civilization that learned to manipulate and direct these biological capabilities could potentially achieve advanced technology without ever developing metallurgy or fossil fuel combustion. Such a civilization would be based on bioengineering, on the selective breeding and genetic modification of organisms to perform desired functions. This is not purely speculative. Human civilization has engaged in bioengineering for thousands of years through selective breeding of crops and animals. Modern dogs, extraordinarily diverse in size and form, are all descended from wolves domesticated and selectively bred over approximately 15,000 years. Corn, the maize that is now a global staple crop, was bred from teosinte, a wild grass that barely resembles the modern crop, through thousands of years of selection by indigenous Americans. Modern biotechnology has accelerated this process through direct genetic modification. Bacteria are engineered to produce human insulin, spider silk proteins, and industrial enzymes. Yeast are modified to manufacture biofuels and pharmaceuticals. Plants are given traits that make them resistant to pests or able to grow in marginal soils. Animals are cloned and modified for research and agricultural purposes. But current biotechnology is built upon foundations of chemistry, genetics, and molecular biology that required centuries of scientific development and industrial infrastructure. Could a civilization develop sophisticated bioengineering without first passing through an inorganic industrial phase? The answer might be yes, given different evolutionary starting points. Imagine a species that evolved with an intuitive understanding of biological processes in the way humans have an intuitive grasp of physical mechanics. Just as humans can intuitively predict trajectories and judge distances, skills honed by evolution for throwing and navigating. This hypothetical species might intuitively understand growth, heredity, and biological modification. Such a species, through careful observation and experimentation, might discover principles of selective breeding very early in their cultural development. They might learn to cultivate organisms not just for food, but for materials, tools, and structural purposes. Over generations, this bioengineering would become increasingly sophisticated. Consider what might be achieved. Organisms could be bred to produce fibers of specific strengths and properties, creating living materials stronger than any synthetic polymer. Plants could be modified to grow into desired shapes, becoming living architecture that continuously maintains and repairs itself. Microorganisms could be cultivated to perform chemical transformations, acting as biological factories, producing compounds useful for technology or medicine. Bioluminescent organisms could provide illumination without fire or electricity. Organisms with electrical generation capabilities could be enhanced to provide power for other biological systems. Venomous or poisonous species could be bred for defense or for hunting. Organisms could be engineered to concentrate and purify specific minerals from the environment, providing access to materials without mining or smelting. Communication technology could be biological. Organisms that produce complex chemical signals could be used for long-distance messaging. Species with remarkable memory capacities could be bred to serve as living information storage. The entire technological infrastructure of such a civilization would be alive, a vast network of interconnected organisms performing functions that our civilization achieves through machines. What would be the signature of such a civilization in the geological record? The answer is profoundly uncertain, likely minimal to non-existent. Living structures decay upon death or abandonment, returning to the environment as organic matter subject to normal decomposition processes. Genetically modified organisms, without continued selective pressure to maintain artificial traits, would likely revert to something resembling their wild ancestors within a few generations. Chemical signatures might persist. Waste products from biological processes might create unusual concentrations of certain compounds in sediments. Isotope ratios might be affected if the civilization's organisms were concentrating specific isotopes. But these signatures would be subtle and highly localized, easily attributed to natural biological processes without additional context. There might be indirect evidence. A bioengineered civilization would likely modify its environment extensively, altering ecosystems to favor the organisms it relied upon. This might create unusual patterns in the fossil record, sudden appearances of domesticated species, range shifts not explained by climate change, extinction of wild populations of species that were later replaced by domesticated variants. But interpreting these patterns as evidence of civilization would be challenging. Species distributions change for many reasons. Extinctions occur continuously throughout the fossil record. New species evolve and spread. Without the cultural context to explain the patterns, they would likely be attributed to natural ecological changes. A bioengineered civilization might also leave architectural remains if it used organisms to construct large structures. Coral reefs, built by countless individual polyps over thousands of years, create massive limestone structures that are preserved in the geological record. A civilization that directed similar processes could potentially build structures that would fossilize. But distinguishing between a natural reef and an artificially directed one would be extraordinarily difficult. Both would be made of calcium carbonate deposited by organisms. Both would show growth patterns and cellular structures consistent with biological origin. Unless the artificial reef had unmistakable geometric regularity, or was combined with other clear evidence of intelligent direction, it would likely be classified as natural formation. The possibility of bioengineered civilizations adds another dimension to our uncertainty. Not only must we consider that ancient civilizations might be hard to detect because of the timescales and geological processes involved, we must also consider that they might have used technologies so fundamentally different from ours that we would not recognize them even if preservation were perfect. If a bioengineered civilization existed 100 million years ago, it might have flourished for millions of years, achieving levels of sophistication rivaling or exceeding our own, yet leaving no trace that we would recognize as technological. Its entire existence would be invisible to our searches, not because the evidence was destroyed, but because we do not know what evidence to look for or how to distinguish it from natural biological processes. The information preservation problem. One feature that seems essential to technological civilization is the accumulation and transmission of information across generations. Humans achieve this through writing, recording knowledge in forms that persist beyond individual lifetimes. But writing, as we practice it, requires materials that are not guaranteed to survive geological timescales. Paper degrades rapidly, lasting at most a few centuries in most environments. Papyrus, parchment, and vellum are similarly vulnerable to moisture, temperature, and biological decay. Clay tablets are more durable, potentially surviving thousands of years if fired, but even these can be broken, eroded, or transformed by geological processes given sufficient time. Stone inscriptions offer better durability. The hieroglyphs carved into Egyptian monuments have survived for thousands of years, still readable after exposure to wind, sand, and sun. But even stone weathers. Softer stones like limestone dissolve slowly in acidic rainwater. Harder stones like granite can crack from thermal expansion and contraction, or be abraded by wind-blown particles. Over millions of years, even the deepest carving would be eroded away. Digital storage, paradoxically, is even more fragile than ancient methods. Magnetic media degrade within decades. Optical discs are vulnerable to oxidation and delamination. Solid-state storage can lose data through charge leakage over years to decades. And even if the physical medium survived, reading the data would require compatible technology and knowledge of the encoding formats, both unlikely to persist beyond the civilization that created them. This presents a profound challenge. How does any civilization preserve information across geological time? The answer may simply be that it does not. Information, unlike some physical and chemical markers, may be inherently transient, unable to survive the passage of deep time regardless of the encoding method. But perhaps there are exceptions. The structure of DNA itself is an information storage system that has persisted across billions of years of evolution. The genetic code, with remarkable consistency, has been passed from generation to generation, modified by mutation and selection, but maintaining continuity from the earliest life to the present day. Could information be encoded in DNA in ways that might persist even after the death of a civilization? In principle, yes. Synthetic DNA can be created with arbitrary sequences, encoding whatever information desired using the 4 bases, adenine, thymine, guanine, and cytosine, as a quaternary digit system. This DNA could be introduced into organisms with high reproductive rates and wide geographic distributions, ensuring multiple copies exist even if local populations are destroyed. But DNA in dead organisms degrades rapidly. The molecular bonds break down through hydrolysis and oxidation, fragmenting the long chains into smaller and smaller pieces. Under ideal conditions, such as frozen environments with minimal moisture, DNA can persist for hundreds of thousands of years. Ancient DNA has been recovered from permafrost and from bones in caves. But beyond approximately 1 million years, even under the best conditions, DNA degrades to the point where only tiny fragments remain, insufficient to reconstruct original sequences. Living organisms maintain and replicate their DNA, constantly repairing damage and creating new copies. But the information they preserve is shaped by selection. Sequences that do not contribute to survival and reproduction are subject to drift and will eventually be lost or altered beyond recognition. Deliberately encoded information, unless it provided some fitness advantage, would not be maintained. Perhaps information could be encoded in features that do provide fitness advantages, but in patterns that are clearly artificial. Imagine an organism engineered to have a specific genetic sequence that serves a biological function, but also, when decoded properly, contains a message. The biological function ensures the sequence is preserved by selection, while the message remains invisible to natural processes, but readable to anyone with the key to decode it. But this requires that someone in the future would know to look for such messages and would have the key to decode them. Without that knowledge, the message would remain hidden, even if perfectly preserved. And over millions of years, even sequences under selection pressure will mutate. The message would accumulate errors, eventually becoming unreadable even if the decoding method were known. Another approach might be to encode information in stable isotope ratios in minerals. Certain minerals can incorporate elements in specific ratios when they form, and these ratios can be extremely stable over geological time. If a civilization could precisely control the isotope ratios during mineral formation, they might create patterns that encode information, but this would require extraordinary precision in isotope separation and mineral synthesis, likely representing very advanced technology. And the encoding would be extremely inefficient. Each mineral grain might store only a few bits of information, and millions of grains would be needed for even a simple message. The minerals would need to be collected and analysed together, requiring someone in the future to recognise that the isotope patterns were artificial and to gather enough samples to reconstruct the message. The fundamental problem is that information, to be useful, must be both preserved and interpretable. Preserving the physical medium is extraordinarily difficult across geological time, but even if preservation occurs, interpretation requires shared context, shared language, shared understanding of encoding methods. Without this context, even a perfectly preserved message is meaningless noise. Human civilization has attempted to address this with messages intended for the far future. The nuclear waste warning messages, designed to inform people 10,000 years hence that dangerous materials are buried in specific locations, struggle with this challenge. How do you communicate danger across cultures, languages, and conceptual frameworks that may be radically different from our own? Various approaches have been proposed. Universal symbols based on geometry, narrative pictograms showing cause and effect, physical structures designed to evoke emotional responses like dread or unease, redundant messages in multiple languages and formats. But even 10,000 years is a blink in geological terms. Extending such messages across millions of years seems nearly impossible. Perhaps the only information that could truly survive geological time is information encoded in structures or patterns so fundamental and universal that they would be recognizable to any technological civilization regardless of biological or cultural differences, mathematical constants, physical laws, fundamental aspects of chemistry and physics. These might be encodable in ways that would be recognized as artificial even without specific decoding knowledge. A structure or pattern that violates natural processes, that shows regularities or proportions that could not arise through geology or biology alone, might stand out as clearly artificial. But creating such a structure that would survive millions of years and remain recognizable despite weathering and geological alteration remains an unsolved challenge. The information preservation problem suggests that even if ancient civilizations existed and created vast libraries of knowledge, records of their history, science, and culture, all of that information would be lost, the physical media would decay, the data would be corrupted, the context necessary for interpretation would be forgotten. What might survive are not the stories civilizations told about themselves, but only the barest physical and chemical traces that they existed at all. Traces so minimal and ambiguous that they might be mistaken for natural phenomena. We would know nothing of their thoughts, their art, their science, their struggles. We would not know what they called themselves, or how they understood their place in the universe. All the richness of civilization, everything beyond its physical impact on geology and climate would be erased utterly, leaving only ghosts and shadows in the rocks. The Drake equation applied to Earth. The Drake equation, formulated by astronomer Frank Drake in 1961, is a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It multiplies together several factors: the rate of star formation, the fraction of stars with planets, the number of planets per star system that could support life, the fraction where life actually emerges, the fraction where intelligent life evolves, the fraction that develop technology capable of communication, and the length of time such civilizations remain detectable. The equation was designed for interstellar communication, but it can be adapted to consider civilizations arising sequentially on a single planet. Instead of asking how many civilizations exist simultaneously in the galaxy, we ask, how many civilizations might have arisen sequentially throughout Earth's history? The adapted equation would consider factors like the number of distinct periods in Earth's history suitable for complex life, the probability that intelligence arises in any given period, the probability that intelligence leads to technological civilization, the average duration of such civilizations, and the time required for evolution to produce new intelligent species after previous ones go extinct. Let us work through this with highly speculative but not unreasonable numbers. Complex multicellular life has existed for approximately 600 million years. We might divide this into periods separated by mass extinctions or major environmental changes, giving us perhaps 20 to 30 distinct trials, during which intelligence might evolve. The probability that intelligence arises in any given trial is unknown, but appears to be low based on the fact that it has occurred recognizably only once in Earth's history, but low is not zero. Let us suppose, conservatively, that the probability is approximately 1 in 50 for any given trial period, lasting approximately 20 million years. This would suggest that on average, we might expect intelligence to evolve once every billion years or so. Given Earth's 600 million years of complex life, this would predict less than one instance which matches observation. We know of one case, humans. But this average conceals variation. Probabilities are not guarantees. Random processes can produce clusters of events or long gaps between events. Flipping a coin with a probability of 1 in 50 of showing heads does not guarantee that you will get exactly one head in 50 flips. You might get 0, you might get 3 or 4. The average is 1, but individual trials vary. If intelligence is such a low probability event, arising only once in 20 trials on average, then the probability of it having arisen twice in Earth's history is low, but not negligible. The probability of 3 instances is lower, but still possible. As we move to 4 or 5 instances, the probabilities become very small, though never quite 0. Now consider the duration of civilizations. Human industrial civilization has lasted approximately 250 years so far. If we persist for another few centuries, we might reach 500 to 1,000 years of industrial activity, before either transitioning to something different, achieving sustainability at lower energy levels, or collapsing due to environmental changes or resource depletion. This is extraordinarily brief in geological terms. 1,000 years is less than 1/1,000,000th of Earth's 600 million year history of complex life. A civilization lasting 1,000 years and then going extinct would represent such a tiny fraction of time that finding evidence of it would require extraordinary luck or extraordinarily widespread impacts. But suppose civilizations sometimes persist longer. Suppose some achieve sustainability and last for tens or hundreds of thousands of years before eventually succumbing to climate change, disease, asteroid impact, or other catastrophes. This increases their footprint in time, making detection more probable. There is, however, a trade-off. Longer-lasting civilizations might be more sustainable, with lower energy use and less environmental impact. A civilization that learned to live within its planet's ecological limits might persist for 1,000,000 years, but never create the kinds of dramatic signatures that a brief, intense industrial phase would produce. Sustainability and detectability might be inversely correlated. Another factor to consider is the recovery time after a civilization collapses. If intelligence arose and a civilization developed, then collapsed due to environmental degradation, how long would it take for evolution to produce another intelligent species capable of civilization? This depends on what survives. If the civilization drove itself and many other species to extinction, the surviving lineages would need time to diversify and refill empty niches. Evolution would continue, but starting from a depleted foundation. Tens of millions of years might be required before ecosystems fully recovered, and selection pressures again favoured high intelligence in some lineages. This recovery time creates spacing between possible civilizations. Even if intelligence could potentially evolve more frequently, the aftermath of each civilization creates a refractory period during which the next one is unlikely to emerge. This limits the total number of civilizations that could have arisen in Earth's history. Putting these factors together with very rough estimates, we might conclude that between 0 and 5 civilizations could plausibly have arisen on Earth before humans. 0 is obviously possible, matching the conventional view. But the numbers do not exclude the possibility of a few earlier instances, separated by hundreds of millions of years, each leaving minimal traces that have been erased or are misinterpreted as natural phenomena. The Drake equation, whether applied to the galaxy or to a single planet's history, reveals the profound uncertainty inherent in questions about the frequency of intelligence and civilization. With only one confirmed example, we cannot distinguish between we are unique and we are moderately rare but not unique. The data are consistent with both interpretations, leaving us in a state of fundamental uncertainty. This uncertainty is not a flaw in our reasoning but a consequence of the nature of the question. We are asking about rare, brief events in an immensely long history, events that might leave minimal evidence and for which we have no clear template to guide our search. The absence of confirmed evidence for ancient civilizations does not resolve the uncertainty. It merely confirms that if they existed, they are either very rare or very hard to detect, or both. The Fermi paradox inverted, asking the question locally. The Fermi paradox, named after physicist Enrico Fermi, who allegedly posed the question during a lunch conversation in 1950, asks, if intelligent life is common in the universe, where is everybody? Given the vast number of stars, the apparent commonality of planets, and the age of the galaxy far exceeding the time required for civilizations to develop interstellar travel, we might expect evidence of extraterrestrial civilizations, yet we observe none. Various solutions have been proposed. Perhaps intelligent life is extraordinarily rare. Perhaps technological civilizations tend to destroy themselves shortly after developing advanced technology. Perhaps interstellar travel is far more difficult than science fiction suggests. Perhaps civilizations deliberately avoid contact. Perhaps we are being observed but not contacted. Each solution has implications for how common or rare technological civilization might be in the universe. But we can invert the Fermi paradox and apply it to Earth itself. If conditions for intelligent life and civilization are common, why do we not see evidence of ancient terrestrial civilizations? If intelligence can evolve, why did it apparently evolve only once in 4 billion years of life on this planet? The conventional answer is that intelligence at the level necessary for civilization is extraordinarily difficult to evolve, requiring specific circumstances and a specific sequence of evolutionary innovations unlikely to be repeated. Humans are unique, not because we are the inevitable culmination of evolution, but because we represent an unlikely combination of traits that happen to arise in one lineage but not others. But the Silurian hypothesis and related considerations suggest an alternative. Intelligence might have evolved other times, civilizations might have developed, but they were brief and left minimal traces that we have not found or have not recognized. The absence of evidence is not necessarily evidence of absence, particularly when dealing with geological timescales that erase evidence so effectively. This inverted Fermi paradox becomes more pressing when we consider that the great filter, the hypothetical barrier that prevents life from becoming spacefaring and abundant, might lie behind us rather than ahead. If the filter is the origin of life itself, or the evolution of complex multicellular organisms, or the development of intelligence, then having passed these barriers, we might expect many civilizations to arise on any planet that clears them. But if civilizations commonly arise and commonly collapse, each leaving minimal traces, then Earth might have hosted multiple civilizations without retaining clear evidence of them. Each civilization would face its own, but if civilizations commonly arise and commonly collapse, each leaving minimal traces, then Earth might have hosted multiple civilizations without retaining clear evidence of them. Each civilization would face its own great filter in the form of sustainability challenges, environmental limits, or catastrophic events, and most would fail, disappearing into geological time. This perspective changes how we think about our own future. If we are not unique, if civilizations have risen and fallen before us, then our own trajectory becomes less certain. We cannot assume that intelligence inevitably leads to spacefaring permanence. We might instead be one more iteration in a long series of attempts, most of which end in collapse and extinction. But there is a paradox here. If civilizations commonly arise, why has no civilization managed to become truly permanent, spreading throughout the solar system or beyond, establishing a presence so vast that evidence would be unmistakable? Even if individual planetary civilizations are ephemeral, why do we not see evidence of one that succeeded in becoming multiplanetary or interstellar? Several answers present themselves. Perhaps the leap from planetary to spacefaring civilization is extraordinarily difficult, representing another great filter that few or no civilizations successfully navigate. The challenges of living in space, of establishing self-sustaining colonies on other worlds, of travelling between stars, might be far greater than our science fiction imagines. Or perhaps civilizations that become spacefaring tend to abandon their homeworlds, spreading throughout the solar system or beyond but leaving the original planet to recover naturally. After millions of years, their home planet would show no evidence of their existence, while their presence elsewhere in the solar system might persist. This suggests a search strategy. If ancient civilizations existed and some became spacefaring, we should look not only in Earth's geological record but also on the Moon, Mars, and other bodies in the solar system, where geological processes are less destructive. The Moon, lacking atmosphere and plate tectonics, preserves its surface for billions of years. Structures built on the Moon hundreds of millions of years ago might still be recognizable today. So far, searches of the Moon's surface, both by telescopic observation and by rovers and landers, have found no evidence of artificial structures, but the searches have been limited, covering only tiny fractions of the surface. Vast regions remain unexamined in detail, it is premature to conclude definitively that no evidence exists. The inverted Fermi paradox applied to Earth's history leaves us with uncomfortable ambiguity. We cannot prove ancient civilizations existed, but neither can we confidently rule them out. The question remains open, suspended between the limits of our knowledge and the vastness of what we cannot know about the deep past. The Moon as archive, a more stable record. The Moon, Earth's only natural satellite, offers something our own planet cannot: a stable, unchanging surface where evidence might persist for billions of years. Unlike Earth, with its atmosphere, water and tectonic activity constantly reshaping the surface, the Moon is geologically dead. What happens on the Moon stays on the Moon, preserved in a vacuum, protected from the erosion that would destroy it on Earth. The Moon's surface is ancient. The lunar highlands, the bright regions visible from Earth, are composed of anorthosite rock dating to approximately 4.5 billion years ago, formed when the Moon's magma ocean crystallized shortly after its formation. The darker maria, the seas, visible as dark patches, are basaltic lava flows that filled large impact basins between 3.9 and 3.1 billion years ago. Since the maria formed, the Moon's surface has changed only through the slow accumulation of impact craters and the gradual mixing of surface material by micrometeorite impacts, a process called space weathering. But these processes, while continuous, are slow. A structure built on the lunar surface would remain recognizable for hundreds of millions of years, possibly billions, depending on its size and location. This makes the Moon an ideal archive for evidence of ancient civilizations, if any achieved spacefaring capability. A civilization that established even a brief presence on the Moon might have left traces that would still be detectable today: landing sites, mining operations, structures, debris. Some researchers have proposed searching for such traces. The term lunar archaeological survey has been used to describe systematic searches of lunar imagery for anomalous features that might represent artificial structures. So far, no confirmed examples have been found, but the searches have been limited in scope. High-resolution images from the Lunar Reconnaissance Orbiter have covered much of the Moon's surface at resolution sufficient to detect objects several meters across. At this resolution, any substantial structure would be visible, but smaller artifacts, anything less than a few meters, would be invisible in orbital imagery and would require surface exploration to detect. There is also the question of what we should be looking for. Human-built structures on the Moon, the Apollo landing sites, appear as small clusters of bright and dark spots in orbital images, the spacecraft and equipment contrasting with the surrounding regolith. But structures built by a non-human civilization might not resemble these. They might be partially buried, degraded by micrometeorite impacts, or constructed from materials that do not create strong visual contrast. Certain features might be more recognizable: linear arrangements of objects or structures, geometric patterns, regularly spaced excavations or mounds. All would be difficult to explain through natural processes. The Moon's geology does not create such patterns. Impact craters are circular or elliptical, not linear. Volcanic features are irregular. Regular geometry strongly suggests artificial origin. Another potential marker is the presence of materials that do not naturally occur on the Moon. The lunar surface is depleted in water, organic compounds, and many metals compared to Earth. If a civilization mined the Moon for resources or brought materials from elsewhere, these might create chemical or isotopic anomalies detectable through spectroscopic analysis. There is also the intriguing possibility of artifacts inside lunar lava tubes. These are tunnel-like voids formed when lava flowed through solidified crust, creating underground passages that can extend for kilometers. Lava tubes on the Moon would be protected from micrometeorite impacts and radiation, making them ideal locations for habitats or storage. An ancient civilization might have used lunar lava tubes for exactly these reasons. Structures built inside lava tubes would be invisible from orbit, detectable only by entering the tubes or by carefully analyzing gravitational anomalies or radar data that might reveal large voids. Several lunar lava tubes have been identified from orbit through collapsed sections that create skylights, openings in the ceiling that reveal the void below. These skylights show that the tubes can be enormous, some potentially large enough to contain entire cities. But exploring these tubes requires landing missions with specialized equipment, investigations that have not yet been conducted. The Moon also preserves regolith, the layer of broken rock and dust covering the surface, in a relatively undisturbed state. Footprints from the Apollo missions remain visible today, looking nearly as crisp as when they were first made. This preservation suggests that any disturbance of the lunar surface would remain visible for extraordinary lengths of time. A mining operation, for instance, would create excavations, piles of processed and discarded material, and tracks from machinery, all of which would remain visible for millions of years. The absence of such features in examined regions suggests either that no such operations occurred in those areas, or that they occurred so long ago that subsequent micrometeorite bombardment has obscured the traces, which would require timescales exceeding several billion years. But again, the searched areas represent only a small fraction of the Moon's total surface. Most regions have been examined only at relatively low resolutions. Vast areas, particularly on the far side of the Moon, which is never visible from Earth and has been less extensively mapped, remain largely unexplored. There is also the possibility that evidence exists but has been misinterpreted. Unusual features in orbital imagery are often explained as natural geological formations without detailed investigation. While this is usually correct, there remains the possibility that some features might be artificial but dismissed due to the presumption that no artifacts should exist on the Moon. The scientific principle of parsimony, Occam's razor, suggests that we should prefer the simplest explanation that fits the evidence. Natural explanations for lunar features are simpler, requiring no assumptions about ancient civilizations, but parsimony can lead us astray if we over-apply it, dismissing possibilities as too unlikely to consider seriously when the actual probability is unknown. The Moon, as a potential archive, offers both promise and challenge. It could preserve evidence that Earth's geology would erase, but that evidence would be difficult to find without extensive systematic searching, and would be easy to overlook or dismiss if we do not know precisely what we are looking for or where to search. As our exploration of the Moon expands in the coming decades, with new missions from multiple nations and private entities, we will have increasing opportunities to search. Perhaps these searches will confirm that the Moon is lifeless and has always been so, devoid of any trace of visitation, or perhaps in some overlooked crater or hidden lava tube, we will find something that changes our understanding of Earth's history and our place in the long story of intelligence in the cosmos. Mars and the question of lost Martian civilizations. Mars, the fourth planet from the Sun, has long captured human imagination as a possible abode of life and perhaps intelligence. In the late 19th and early 20th centuries, astronomers believed they observed canals on Mars, straight lines interpreted as irrigation systems built by a desperate civilization facing a dying planet. These canals proved to be optical illusions, tricks of perception, and atmospheric distortion, but the fascination remained. We now know that Mars is cold, dry, and apparently lifeless at its surface. Its atmosphere is thin, less than 1% the density of Earth's, composed primarily of carbon dioxide. Surface temperatures average approximately -63 degrees Celsius, cold enough that carbon dioxide freezes out of the atmosphere at the poles. Liquid water cannot exist at the surface due to the low atmospheric pressure, but Mars was not always so inhospitable. Evidence from orbiting spacecraft and surface rovers reveals that Mars once had a thicker atmosphere, warmer temperatures, and liquid water flowing across its surface. Ancient river valleys, lake beds, and possible ocean basins indicate that early Mars, approximately 3.5 to 4 billion years ago, was more Earth-like. This raises a fascinating question. If Mars was more habitable in the distant past, could life have arisen there? Could that life have evolved intelligence? Could a Martian civilization have developed, only to disappear as the planet's environment deteriorated? The conventional answer is no. We have found no evidence of life on Mars, past or present. Extensive searching by rovers and landers has revealed no fossils, no chemical signatures of life, no structures that might indicate biological or technological activity. Mars appears to be, and always to have been, sterile. But this absence of evidence faces the same challenges discussed earlier for Earth. Mars's surface has been heavily modified over billions of years. Vast volcanic eruptions resurface large regions. Dust storms redistribute surface material. Impacts from asteroids and comets create craters and ejecta blankets that bury older surfaces. Erosion, while slower than on Earth due to the thin atmosphere, still operates over geological time. If a Martian civilization had existed billions of years ago, during Mars's more hospitable period, what traces might remain? Physical structures would be degraded by impacts and erosion, but might still leave recognizable ruins if they were large enough, and if we searched in the right locations. The absence of plate tectonics on Mars means that surface features can persist much longer than on Earth, offering better preservation potential. Chemical signatures might persist in sedimentary rocks formed in ancient lakes. If Martian life had biochemistry similar to Earth life, it might have created isotopic fractionations similar to those we associate with biological activity. Fossilized microorganisms might exist in rocks formed in aqueous environments. But a technological civilization would leave more distinctive traces. Mining operations, if they occurred, would create excavations and waste piles that might still be visible despite billions of years of erosion. Refined materials, especially if they were buried and protected from surface weathering, might survive in detectable concentrations. There is also the possibility of subsurface artifacts. Mars has extensive lava tubes similar to those on the Moon, formed by flowing lava during the planet's volcanic era. These tubes, protected from surface weathering, might preserve evidence that surface locations would not. A civilization facing a deteriorating surface environment might have moved underground, creating habitats in lava tubes or excavated chambers. Exploring these subsurface environments would require missions far more capable than current rovers, which are limited to surface exploration. It would require drilling equipment, subsurface penetrators, or human expeditions capable of entering and exploring underground chambers. Some researchers have proposed looking for anomalous chemical signatures in the Martian atmosphere as potential markers of subsurface life or activity. Methane, detected intermittently by orbiters and rovers, might be produced by biological processes, though geological sources are also possible. More exotic possibilities include industrial chemicals that might be released from underground facilities, though no such chemicals have been detected. There is also the question of what happened to a hypothetical Martian civilization. Mars lost most of its atmosphere over billions of years, probably due to solar wind stripping after the planet's magnetic field shut down when its core cooled. As the atmosphere thinned, temperatures dropped, and water either froze into the subsurface or was lost to space. A civilization facing this gradual deterioration would have had millions of years to respond. They might have developed technology to survive in increasingly harsh conditions, moving underground or developing sealed habitats. Or they might have attempted to leave Mars, developing spaceflight to migrate to more hospitable worlds. If they achieved spaceflight, they might have colonized other bodies in the solar system, or even traveled to Earth. This raises the intriguing possibility that life on Earth might have Martian origins, that microorganisms or even complex life might have been transferred from Mars to Earth via meteorites ejected by impacts. This hypothesis, called panspermia, has some support from the discovery that Mars meteorites do reach Earth, and that microorganisms can potentially survive the journey, protected within rock interiors from the radiation and cold of space. If life originated on Mars when conditions were favourable and later spread to Earth, then we might be, in a sense, descendants of Mars. But this does not require a Martian civilization. Natural transfer via meteorites could occur regardless of whether intelligence ever evolved on Mars. The evidence for panspermia, while intriguing, is not conclusive, and the hypothesis remains speculative. The search for evidence of ancient Martian civilizations faces enormous challenges. Mars's surface area is approximately equal to Earth's land area, vast regions to search with limited robotic missions. Most of the planet remains unexplored at the resolution necessary to detect ruins or artifacts. Subsurface environments are almost entirely unexplored. Current missions focus on searching for signs of ancient microbial life, not civilizations. The assumption, reasonable given the absence of any evidence to the contrary, is that if life existed on Mars, it was simple, microbial, never progressing beyond the most basic forms. This assumption guides where we search and what we search for, but assumptions can be self-fulfilling. If we search only for microbial life, we will find only evidence of microbial life, if we find anything at all. Evidence of more complex life or intelligence might exist but remain undetected because we are not looking for it in the right places or in the right ways. As human missions to Mars become more feasible in the coming decades, opportunities for more extensive exploration will arise. Humans can explore far more rapidly and flexibly than rovers, can make intuitive judgments about where to search, can access locations too dangerous or difficult for robots. Perhaps human explorers will discover something that robotic missions missed. Or perhaps Mars is and has always been lifeless, a cautionary tale of a planet that began with promise, but failed to maintain conditions suitable for life or intelligence. Either answer would be profound, teaching us something fundamental about the emergence of life and intelligence in the cosmos, the vastness of what we do not know. Throughout this exploration, we have confronted again and again the limits of our knowledge. The geological record is incomplete, fragmentary, biased towards certain environments and certain periods. Preservation is the exception rather than the rule. Chemical signatures are ambiguous, interpretable as either natural or artificial depending on assumptions. Physical artifacts, even if they survive burial, might be unrecognizable after millions of years of alteration. These limitations mean that our understanding of Earth's deep past is necessarily uncertain. We see snapshots, brief glimpses, disconnected fragments from which we attempt to reconstruct a coherent narrative, but large portions of that narrative are missing, filled in by inference, extrapolation, and assumption. Consider how much of Earth's surface remains unexplored. The ocean floor, covering 71% of the planet, has been mapped in detail for only a small fraction of its area. Most is known only through low-resolution sonar mapping sufficient to reveal major features like underwater mountains and trenches, but missing anything smaller than several hundred meters across. Deep ocean sediments, which might preserve evidence of ancient events better than terrestrial environments, have been sampled at only a few thousand locations worldwide. Each core sample, a cylinder of sediment typically a few centimeters in diameter and several meters long, represents a single point in space and time. The chances of such a sample intersecting evidence of a brief, localized event from millions of years ago are vanishingly small. On land, most of Earth's surface has been examined geologically but not exhaustively. Remote sensing provides overviews, but detailed examination of rock formations, particularly those that might be of unusual age or composition, requires fieldwork by trained geologists. The number of such experts is limited, and the area to be examined is vast. Even well-studied regions contain surprises. New fossil discoveries occur regularly, sometimes revealing organisms or ecosystems that were completely unknown previously. Each discovery revises our understanding of what was possible at different points in Earth's history. What we think we know remains provisional, subject to revision as new evidence emerges. Dating techniques, while sophisticated, have resolution limits that leave room for hidden events. A sedimentary layer dated to 100 million years ago, plus or minus 2 million years, contains within its uncertainty window more time than the entire existence of the genus Homo. Civilizations could rise and fall within that window, leaving traces in layers we have not yet sampled or interpreted. There is also the challenge of recognizing what we do not expect. Science progresses by forming hypotheses and testing them against evidence, but if we have no hypothesis suggesting that ancient civilizations might exist, we will not design tests to look for them. Evidence might exist but remain unrecognized because it does not fit any expected pattern. This is not to suggest that we should accept extraordinary claims without extraordinary evidence. The principle of skepticism remains valid. Claims of ancient civilizations should be held to high standards of proof, requiring multiple lines of evidence, reproducibility, and rigorous exclusion of alternative explanations. But skepticism can become dogmatism if it hardens into the presumption that certain possibilities are so unlikely as to not merit serious investigation. The history of science includes numerous examples of hypotheses initially dismissed as impossible or absurd that were later confirmed when evidence became available. Continental drift, the idea that continents move across Earth's surface, was dismissed by most geologists for decades after Alfred Wegener first proposed it in 1912. The mechanism was unknown, and the concept seemed to violate what was understood about Earth's structure. Only in the 1960s, when seafloor spreading was discovered and plate tectonic theory developed, did continental drift become accepted. The impact hypothesis for the extinction of the dinosaurs faced similar resistance. The idea that an asteroid impact caused the end Cretaceous extinction was proposed in 1980 by Luis and Walter Alvarez, based on the discovery of an iridium anomaly in the geological boundary. Many paleontologists initially rejected this hypothesis, preferring explanations based on volcanism or gradual climate change. Only after the discovery of the Chicxulub impact crater in the 1990s did the impact hypothesis gain widespread acceptance. These examples teach us that absence of evidence, especially in fields where preservation is poor and observations are incomplete, should be interpreted cautiously. The evidence for continental drift and for impact-caused extinctions existed in the geological record long before scientists recognized it. The delay in acceptance reflected not the absence of evidence, but the difficulty of recognizing and correctly interpreting fragmentary clues. Could we be in a similar situation regarding ancient civilizations? Might evidence exist but remain unrecognized because we lack the framework to interpret it correctly? The answer is uncertain, but the possibility cannot be dismissed without more extensive searching than has yet been conducted. The vastness of what we do not know extends beyond Earth. Our solar system contains myriad worlds, most unexplored in detail. The asteroid belt, with hundreds of thousands of objects larger than a kilometre across, has been visited by spacecraft at only a handful of targets. The Kuiper belt and Oort cloud, containing trillions of icy bodies, remain almost entirely unknown. Could ancient artifacts exist on asteroids or comets, placed there by civilizations from Earth or elsewhere? The environments are harsh, but vacuum and cold preserve materials well. An artifact placed on an asteroid billions of years ago might remain largely intact, protected from the weathering that would destroy it on Earth. But finding such artifacts would require an extensive, systematic survey of countless objects, an undertaking far beyond current capabilities. We are only beginning to explore our solar system in detail, and the timescales for comprehensive surveys extend decades or centuries into the future. The question of ancient civilizations remains open, suspended in the vast space between what we know and what we can know, given current methods and resources. We cannot prove they existed, but neither can we confidently assert they did not. The uncertainty is not a failure of science, but a recognition of its limits when dealing with deep time and incomplete evidence. Implications for our own future. If we accept, even as a possibility, that civilizations might have arisen and disappeared before humanity, what does this imply for our own future? The question shifts from academic curiosity to existential concern, for it suggests that technological civilization is not necessarily permanent, not inevitably progressive, but rather fragile and perhaps temporary. Human history, viewed optimistically, appears as a narrative of progress. From stone tools to agriculture, from writing to industrialization, from steam engines to computers, each innovation builds upon previous ones, creating cumulative advancement. This narrative encourages the belief that progress will continue, that future generations will be more advanced, more capable, wiser than ourselves. But this narrative is selective, emphasizing successes while downplaying setbacks. It ignores the civilizations that did collapse, the knowledge that was lost, the technologies that were abandoned. The Library of Alexandria burned, destroying countless texts. The Roman Empire fell, and many engineering capabilities were lost for centuries in Europe. Entire civilizations, from the Maya to the Easter Islanders, collapsed due to environmental pressures or internal conflicts. These collapses were not complete extinctions of humanity, but rather regional or civilizational failures, after which recovery occurred, often building on knowledge preserved elsewhere. But on a planetary scale, with a global civilization, recovery might not be possible. If our technological civilization collapsed, if the environmental system supporting billions of people failed, the die-off could be severe enough that survivors lacked the resources and knowledge to rebuild. The concept of a resource ratchet makes this particularly concerning. Human civilization has already extracted the most easily accessible fossil fuels, the highest grade ores, the richest deposits of essential minerals. A future post-collapse society, attempting to industrialize again, would face far greater challenges accessing resources than we did during our first industrialization. Coal seams near the surface have been mined out. Oil reservoirs requiring only simple drilling have been depleted. Copper ores rich enough to smelt with pre-industrial technology are increasingly rare. A post-collapse civilization would need more advanced technology to access remaining resources, but developing that technology requires the resources they cannot easily access. This creates a potential trap, a situation where collapse becomes irreversible because the conditions that enabled initial industrialization cannot be replicated. If we fail, if our civilization collapses, it might be the last technological civilization Earth ever sees, not because intelligence cannot re-evolve, but because the resource base necessary for industrialization would be permanently depleted. This suggests a profound responsibility. If we are, if not the first, then perhaps the last chance for Earth-based technological civilization, then our choices matter not only for ourselves, but for the deep future of intelligence on this planet. Sustainability is not merely an environmental concern, but an existential necessity. The environmental changes we are causing, atmospheric carbon dioxide levels rising at rates unprecedented in millions of years, biodiversity declining at rates approaching mass extinction events, plastic and chemicals accumulating in ecosystems globally, are creating signatures that will be visible in the geological record. We are leaving our mark on Earth's geology regardless of whether we survive as a species. But the meaning of that mark depends on what comes after. If we navigate the challenges of the 21st century, transitioning to sustainable energy sources, stabilizing population, learning to live within Earth's ecological limits, then the Anthropocene might be viewed as a brief transition period, a growing pain in the maturation of technological civilization. If instead we fail, if climate change or ecological collapse or nuclear war or other catastrophes cause widespread die-off and civilizational failure, then the Anthropocene becomes a cautionary tale, a marker in the rock record of a species that developed technology but could not control it, that transformed its world but could not sustain the transformation. And in either case, whether we view ourselves as the first or the latest in a series of attempts, the deep time perspective counsels humility. The Earth existed for billions of years before us. It will exist for billions more after we are gone one way or another. Our presence is brief, our impact temporary in geological terms. The planet will continue, will heal, will change, indifferent to our fate. This is not nihilistic, but rather clarifying. It places our struggles in context, reminds us that the universe does not revolve around human concerns, that we are participants in a vast cosmic story rather than its culmination. We matter, but not as much as we sometimes believe. Our civilizations rise and fall, but the processes that gave rise to us, evolution and geological change, and the flow of energy through ecosystems, these continue regardless. There is a strange comfort in this perspective. If ancient civilizations rose and fell, if we are not unique but rather one instance of a recurring phenomenon, then our potential failure is not unprecedented, not a cosmic tragedy, but rather a natural risk inherent in technological intelligence. And yet, knowing this risk, we might be better positioned to avoid it, to learn from the fate of hypothetical predecessors we can never know, but whose absence speaks volumes. The question of ancient civilizations ultimately is not about the past, but about the future. It asks whether intelligence and technology represent a stable attractor state, something that once achieved tends to persist and expand, or whether they are temporary, unstable configurations that tend toward collapse. The answer will be written not in the rocks of the deep past, but in the choices we make in the present and near future, choices whose consequences will echo far beyond our individual lifetimes. The search continues. Future investigations. Despite the challenges and uncertainties outlined throughout this journey, the search for evidence of ancient civilizations need not end in despair or resignation. While definitive proof may be extraordinarily difficult to obtain, improved methods and expanded searches could narrow the range of uncertainty and perhaps reveal unexpected discoveries. One promising avenue involves more sophisticated chemical and isotopic analysis of sedimentary rocks. Current techniques can detect anomalies in carbon, nitrogen, and sulfur isotopes, but higher precision instruments and more extensive sampling could reveal subtler patterns. If ancient industrial activity left chemical fingerprints, more sensitive detection might find them even when they are faint or localized. Machine learning and artificial intelligence offer tools for pattern recognition that might identify anomalies humans would overlook. Training algorithms on geological and paleontological databases, then tasking them to search for unusual patterns that do not fit natural explanations, might reveal candidates for further investigation. The key is to search without preconceptions, allowing the algorithms to identify patterns we would not think to look for. expanded exploration of the ocean floor, both through improved seafloor mapping and through more extensive sediment coring, could reveal environments and events currently unknown. The deep ocean, particularly near mid-ocean ridges and in deep basins where sediment accumulates, might preserve evidence from periods poorly represented in terrestrial rocks. Future missions to the Moon and Mars will provide opportunities to search for evidence in environments where preservation is better than on Earth. High-resolution mapping of the entire lunar surface, exploration of lava tubes, sample return missions from carefully selected sites, all might reveal traces of ancient activity. The same applies to Mars, where human missions in the coming decades could explore in ways impossible for current robotic missions. There is also the possibility of searching for evidence in places we have not yet considered. Lagrange points, gravitationally stable locations in the Earth-Moon system, could potentially host debris or artifacts that have remained there for millions of years. Space-based observation platforms might detect anomalous objects in unusual orbits that warrant investigation. Asteroid mining, as it develops, might inadvertently discover evidence if ancient civilizations engaged in similar activities. Examining the composition and structure of asteroid mining sites, looking for evidence of previous extraction, might reveal whether resources were previously exploited and when. The development of new dating techniques could improve our ability to resolve brief events in the geological past. Current methods have resolution limits, windows of uncertainty that can span millions of years. Improved techniques, perhaps based on new isotopic systems or on statistical methods for interpreting multiple dating results together, might narrow these windows and reveal structure in what currently appears as uncertainty. There is also potential in interdisciplinary collaboration. Combining expertise from geology, paleontology, geochemistry, archaeology, astrobiology, and other fields might generate insights that single disciplines would miss. An anomaly that seems explicable within one field might be puzzling when considered from multiple perspectives simultaneously, prompting deeper investigation. Citizen science projects, enlisting thousands or millions of volunteers to examine images from orbiting spacecraft or to analyze data from scientific instruments, could vastly expand the scope of searches. Human pattern recognition remains superior to algorithms in many contexts, and distributing the work of examining vast datasets among many participants makes previously impossible tasks feasible. There is also value in simply maintaining the question as an active area of inquiry, even if progress is slow and definitive answers remain elusive. Science benefits from asking questions without knowing in advance what the answers will be. The search for ancient civilizations, even if ultimately unsuccessful, generates new knowledge about Earth's history, about the limits of preservation and detection, about the nature of intelligence and technology. And there remains the possibility, however remote, of a transformative discovery. A structure on the Moon that cannot be explained naturally. An isotopic anomaly in ancient sediments that defies all conventional interpretations. A chemical signature requiring industrial processes to explain. Such a discovery, if it occurred and withstood rigorous skeptical examination, would revolutionize our understanding not only of Earth's past, but of the nature and frequency of intelligence in the universe. Until such a discovery occurs, or until searches become exhaustive enough to confidently rule out the possibilities, we remain in a state of informed uncertainty. We know that ancient civilizations are theoretically possible, that the geological record is incomplete enough to hide evidence of brief, localized phenomena, that preservation and detection face profound challenges across deep time. We also know that no confirmed evidence currently exists, that natural explanations are simpler and sufficient for all observed phenomena, that the burden of proof rests on those claiming extraordinary events rather than on those maintaining conventional interpretations. The question remains open, suspended between plausibility and proof, between hypothesis and confirmation. It is a question that touches on deep issues of human meaning and cosmic context, that challenges our assumptions about our own uniqueness and importance, that forces us to confront the vastness of time and the limits of our knowledge, and perhaps that uncertainty itself is valuable. It reminds us that our understanding of the world, confident and detailed though it may be in many domains, remains provisional, incomplete, subject to revision as new evidence emerges. It encourages intellectual humility, a recognition that what we do not know far exceeds what we do know, particularly when we venture into the deep past or the deep future. The search continues, not because success is guaranteed, but because the question matters, because answering it one way or another would teach us something profound about life, intelligence, and our place in the long story of Earth and the cosmos. Silence and the weight of possibility. As we emerge from this journey through deep time, through layers of rock and epochs of life, through the mathematics of probability and the ambiguities of evidence, we are left not with answers but with refined questions, sharper awareness of what we do not and perhaps cannot know. The silence of the geological record, the absence of clear evidence for ancient civilizations, speaks with multiple voices. It might be the silence of emptiness, confirming that we are indeed the first, the only, the unprecedented emergence of technological intelligence on Earth. This interpretation aligns with conventional scientific understanding and requires no additional hypotheses beyond those already well established. But it might also be the silence of erasure, the absence left when time destroys evidence, when processes of burial and erosion and tectonic recycling obliterate the traces of events that occurred hundreds of millions of years ago. This interpretation is compatible with our understanding of how geological preservation works, with the incompleteness of the fossil record, with the difficulty of detecting brief events across vast timescales. Or it might be the silence of ignorance, evidence existing but unrecognized, patterns present but not yet detected, artifacts preserved but not yet found or not yet interpreted correctly. This interpretation suggests that our searches have been insufficiently comprehensive, our methods not yet sensitive enough, our imaginations too constrained by expectations of what we should find. Each interpretation carries implications. If we are truly the first, then the evolution of intelligence and technology is extraordinarily rare, a confluence of unlikely circumstances that occurred once in 4 billion years. This rarity suggests both uniqueness and fragility, a responsibility to preserve what has emerged only once and might never emerge again if we fail. If ancient civilizations existed but their evidence was erased, then intelligence and technology might be less rare than we assume, perhaps recurring periodically when conditions permit. But the erasure itself carries a message, that geological time is merciless, that even civilizations capable of transforming their world leave only faint traces, that permanence is an illusion, and all our works are temporary. If evidence exists but remains unrecognized, then we live in a state of false certainty, confident in our uniqueness, when we might instead be one iteration among several. This possibility counsels humility, a willingness to question assumptions, an openness to revising our understanding when new evidence emerges or when old evidence is reinterpreted. Perhaps all three interpretations contain elements of truth. Perhaps we are rare but not unique. Perhaps some evidence was, what if humans were not the first civilization on Earth?